because the high toxicity that it has, and also a huge number of fragments that are created. The other particle that was used was ions, but again, they discontinued it because it's very complex to produce, it's not stable at all, and it's very costly. Then let's talk about the difference between conventional radiotherapy and hadron radiotherapy. When I refer here to conventional radiotherapy, I'm referring to photon therapy. And the difference between the particle therapy is that photons, when they interact with human tissue, they attenuated. But the physical process for particles or for ions is different. They lost energy in the pad, and this is visible here. And then they lost energy in the pad. The physics behind is different as well, because photons interact for photoelectric fed, scattering very production. Instead, particles interact with the Coulomb and nuclear interactions with the nucleus. The formula that described the interaction or the energy loss of a particle is the beta-Bloch equation. And usually when we talk about particles, we refer to the shape that the energy deposition throwing along the depth. And this shape that they throw in the path depth is called the Bragg peak. And this is the main characteristic of charged particles, that they deposit the energy in a very particular region. And this type of therapy is commonly known as a target therapy. But particles, apart of deposit the energy, they also fragment. So in this plot, I am showing you how is the relative ionization, or could be also the energy deposition of a carbon ion of 330 MeV per nucleon along the depth in water. This, the red solid line described the energy deposition purely by a primary carbon, which is described by the beta-Bloch equation. But carbons, the nucleus of the carbon can fragment apart, and those fragments can inherit the same energy per nucleon as the primary carbon. So they can keep traveling in the patient, and they can as well interact inside of the patient. This is, so there are characteristics about this heavy or light ion radiotherapy. And the characteristics here is the tail due to the secondary fragments. Okay. So for recap, if you have a light fragments, in this case, carbon, which has 6 neutrons and 6 protons in the nucleus, and these nucleus interact with the anatomy nucleus of in human tissue, both can fragment. But the targets, so the target nucleus, so the target, the nucleus in the tissue, they fragment and they can get excited and they can generate radioactive fragments, but they don't move. Those fragments move very few millimeters. But the projectile, which is in this case the primary carbon, fragment, that the kinetic energy that it has per nucleon is transferred to all the subfragments. And this is the reason why the tail here. Okay, I mentioned about neon, why neon is not used anymore. Because neon has these different characteristics here, because it's so big that it interacts a lot at the entrance, the surface, the skin surface. And a part of that, the fragmentation we describe here by this blue curve, is also higher because it's a bigger nucleus that can undergo fragmentation, and the fragments can again suffer of fragmentation. So in particle therapy, we also refer to this ratio between the beam entrance and the peak. And if the ratio between the peak and the entrance is as small, it's not good for therapy, because all the dose that we wanted to spare at the beam, at the entrance of the beam, then is not achievable when we compare, for instance, when we compare with products. So the dose deposition in the entrance region is considerably lower than the dose in the target region. Okay, so I just described how the energy deposition is how the carbons or protons or charged particles in general deposit the energy in them, but how we irradiate a target region. So here in gray, we have a region that is representing the two. And we need to build up this, we need many of the Bragg peaks to cover this region. So the higher the energy of the charged particles, the deeper it can penetrate into the tissue. So we start to irradiate from the higher energy to the lower energy until the sum up of all energies in the region coverage the dose target in the tube. And this region is called a spread out Bragg peak. The lines that I'm describing here, right, are like a picture of one plane. But if we take a picture of the full pencil beam, what is a pencil beam? A pencil beam are all the particles which has the same energy that are irradiated at the same moment. And if we take a picture along the path to this particle, this is what we're gonna see. Let's take a look to the different energies that I'm presenting here and also to the different depths, because the scales here are not the same. So 50, and this is protons, no carbons. So this is a proton pencil beam of 50 MeV. And the penetration depth in water is approximately 2.2 centimeters. And then if we go to a higher energy, higher the penetration, the higher the energy, higher the penetration. So this is the profile in depth. But now, if we then move to the XY plane, so to the perpendicular plane, how we manage to cover all the area to irradiate in this plane? Well, we irradiate different of those pencil beams until cover the whole the whole target area. The pencil beam has a shape of a double Gaussian, so X and Y are described by the Gaussians. And then we can modify the size of the beam, and it's called the spot. So we can modify the spot size of this beam when it's traveling. And then depending on the size that we defined, we need to define which is the distance between all those Gaussian-shaped pencil beams. So for instance, if we use 3 sigma distance between the pencil beams, we're gonna have this like mountain not homogeneous dose distribution. But instead, in this example, you will make the spot beams closer. The sum up all the Gaussians are gonna give us an homogeneous coverage for those deposition in one plane. Okay, I have spoken about the pencil beam that are a group of particles with the same energy that are irradiated. But I haven't mentioned how we generate those energetic charge particles. There are 2 ways of doing so. The first one is a cyclotron, in which we have a source of the particles in the center, and then by the difference in the oscillating electric field in between the two D's magnets, they accelerate them in between this gap, and then by the magnetic field from the D magnets, they go to this to the root, and the circle continues until the particles reach a maximum energy. So with this method, you have always particles to the maximum energy. But I just mentioned that we need different energies to reach different depths in the patient. In this case, you reach the maximum energy that the cyclotron can give you, and then you put a degradator. The problem with a degrader is that then you have a lot of neutron activation. The advantage of this system that is compact for a proton, for having protons or for producing protons is a 6 meters diameter machine. And so far, just proton machines has been used. Next year, the first carbon cyclotron will be in operation. But the limitation here is that it's more difficult to set certain energy. So the precision of having energy is less. The uncertainty of energy is more. Put in these words. The second option to generate particles up to the theoretical energies that we need is using a synchrotron. So in a synchrotron, you have the source, which is a gas. This gas, for instance, for carbon, is CO2. You separate the carbon for this molecule. Then you take out the electrons because you need charge fragments to be able to accelerate them. The particles with very low energy, because are just static carbons, enter to a pre-acceleration phase in a LINAC, and they gain there some energy. Then they start to be accelerated in the ring on the synchrotron. So there are radio frequency pulse magnets and radio frequency electric fields that make them accelerate, and then the magnet turning, accelerate, turn, accelerate, turn, accelerate. And they undergo that until the energy that you tell the machine that you wanted the particle to be. So the advantage of using a synchrotron is also that the particles, this pencil beam that I told you, that is built for certain amount of carbons or primaries, the ejection of this pencil beam, you can control it. And it's made by poles. So you are taking out parts of the particles that are in the accelerator. And that is better if you wanted to do gating, or gating is when you irradiate just in certain moments to the patient. It's used mainly for lung cancer, and you wait until the respiratory phase is always in the same point, and you irradiate just when the tumor is in the same position. The challenge of the cyclotrons is that they are huge. You need to build their own facility to have a synchrotron. Also, here, the size of the machine depends on the type of particle that you want to accelerate. If you want a massive or more massive charged particle they're accelerating, you need a larger ring. Yes, they are expensive, they expense. The advantage is that you can have multi-ions. So you can basically have different sources of particles, and then you just activate which particles do you want from the molecule that is in the ion. You split the ion type that you want. So for instance, for the CO2 molecule, we get carbons and we get oxygen at the facility here in Heidelberg. Well, but I explained you that we have pencil beams, right? But we need to cover in X and Y different positions. And we do so by deflecting the magnet that is coming out from the ring of the accelerator. So we have a couple of magnets that deflect the beam in the horizontal position, another set of magnets that deflect the beam in the vertical direction. Here I brought you a video. Let's see if it is working. It's a video from the Mayo Clinic in which they explained this method that is called raster scanning. What you are seeing there, the movement is the deflection of the magnets. And the movement in depth is energy changes. Okay. Do you have any questions until here? Feel free to ask me questions because it is important that it's clear the basics. Also by the chat.
From the chat, have questions? No.
No? Okay.
Till now? No.
Okay, so I'm gonna continue. So we know that okay, but I just present you the advantages of the therapy. So we have, it is a target therapy. We can really control where the dose is deposited. We have those fancy systems that we can basically paint the tumor. This therapy is useful for treating complex cases in which there is critical structures surrounding the tumor to irradiate the tumor region. But this therapy also has challenges. And the main challenge here is the stability, the anatomical stability of the patients between the course of the treatment. So we know that usually radiotherapy treatment leads to a couple of days. So here we have an example. The image that you are seeing here of the CT is an anthropomorphic phantom, Sears phantom. And if we irradiate in the day 1 our planned dose with many of those pencil beams reaching the tumor, everything looks fine, right? But what if the patient, in this case our cis phantom, got sick in the day 10 and our cis phantom got a flu, and now the nasal cavity of the patient is full of mucus? Well, the range of the particles, so where the particle stop, this is another important concept in particle therapy, the range is defined where the particle stops, where it has lost all the energy and then stops. The range of the particle will be modified because now it is interacted with this extra tissue that the planet CT didn't have. There is this Bermuda Triangle that describes the range of uncertainties in particle therapy, and the peak, or the one that has the more potential magnitude, is the variations in the anatomy of the patients. The variations can be different, can come from the cavities, which are the more probable, and the ones that have more impact in the dose distribution. But there are some other changes in the anatomy of the patient. The patient can't lost or gain weight. The tumor can grow or shrink. The tissue of the patient can swell. And another variation in the patient that is not a variation in the anatomy, but it's a variation that the machine is not able to see, is the patient misposition. And those variations that are coming from the patient can lead to an underdosage or an overdosage, an underdosage on the tumor region and an overdosage of the organ at risk. In this example that I just present here, which is just, I don't remember exactly by heart, but I think it's 5 grams for silicone that emulate the filling of the cavity in this phantom, lead us to these differences in the dose distribution. We are seeing here in the day 10 that there is an underdosage inside of the target region, and what we are seeing here is just physical dose. So in the particle therapy community, the question is always, but where the particles stop? No. And this is what we call, or the way that we could try to overcome and investigate where the particles stop are called monitoring methods or treatment monitoring methods. There are, in general, 3 big monitoring methods that has been investigated in the last decade and a half. And the idea of the monitoring methods is to design a method in which you don't add any extra dose to the patient. And we can do that in particle therapy because particles undergo many different processes when they interact with the patient. So at the beginning of this presentation, I show you how two nucleus, the projectile one, for instance, a carbon, interacting with the nucleus of human tissue can fragment apart. This is one physical process that happened. But there are other 2 physical processes that could happen. The second one is that some of those fragments or some of those elements are now radioactive. And the other is that when the nucleus fragment, they can get excited. And they don't have, and the way that they release the excitation is by emitting proton gammas. So using the proton gammas, the charged nuclear fragments that, as I mentioned to you, have the same approximately the same energy as the primary, but as they have less mass, they can exit the patient. So we can detect proton gammas exit the patient, fragments exit the patient, and because of the radioactive entities inside, on the patient, they can emit this characteristic positron emission of 511 MeV and are detected by a normal PET machine. There is another way of monitoring, which is with acoustic waves. And this is because when we irradiate a patient with one of those pencil beams, it creates heat, very small heat there, around millikelvin, but it also generates a wave that can be detected by an ultrasound machine. This is not under investigation so actively now. So I'm gonna focus on the 3 monitoring methods that I mentioned at the beginning. So in proton gammas, as I just mentioned, the gammas can exit the patient and we can correlate the number of gammas that are emitted along the pencil beam, because the probability of interaction, the probability of the gammas to be generated increase next to the Bragg peak. But there are different challenges here. The first one is that you need to put a collimator to register just exactly the prone gammas that are ejecting, right, from the region of interest. And then you are receiving gammas from different energies, right? And gammas from interactions with different like surrounded tissue. So the idea here is to correlate the amount of gammas with the range of the particles. There are several groups working on it. Most of them now are working how to increase the detectability. So the work here is more related with the development of or the improvement of some of the detectors. The other method that I mentioned is the annihilation of gamma, so PET. But here one of the challenge was a technical challenge, is because in the first image that I just present here, the beam is coming from the top, right? But usually when we irradiate the patient, we irradiate it from the side. Something that I will show you later is that most of particle therapy centers have horizontal beams and are fixed beams. So this idea of irradiating the patient here is not so common. It's possible, but it's not so common. So there are some research groups around the world. This is a group that has been developing PET detectors for different applications, for mini PETs and so on. They are located in Japan, in Kimat, if I remember correctly. And they come up with an idea of having a hole in between two rows of detectors. The problem here is that they are losing all gammas that could detect here. So they designed another system, which for me is the most created one, in which the ring now is not completely straight, but they shift all the rings. But for it, then they need to develop another method to do the reconstruction of the signal, because in PET it's well defined how the reconstruction is by the coincidence. So you trace a line between the two coincidence points. Then in your sinogram, you have the angle of the trace and the distance to the center. But here, now the ring is not anymore vertical, let's say, it's shifted. And this is one of the challenge there. But the method itself, despite of the technical constraints that the PET monitoring can have, there is a pure problem, because when you irradiate the patient and those radioactive elements, for instance, carbon-11, are in the body, they can't, by the vascularization of the tissue, can be moved. So when you take the patient, and this is another challenge in this technique, either you have a CT inside of your treatment room, either you have a PET CT, sorry, a PET outside of the room, or you have those systems that I just described here, in which you irradiate the patient and at the same time you measure. If you have such as systems in which you irradiate the patient and measure, you are not losing statistics, because you can wait until the time, the lifetime of the radionuclides. So my point here is that the radionuclides has some life, right? And the one that is more intense is carbon 11. And for instance, that one has 22 minutes. If you need to wait until your patient is fully irradiated, which can last up to 10 minutes, and then you move it to another room and you take the image of the PET, you are losing statistics. But also in this time that you need to wait, where the carbon 11 was created, it would be moved by the vascularity of the environment of the tissue. And this is called washed out. So you cannot correlate really the dose, the position, or where the particles stop with the signal of the PET. So in PET, you have always to make a Monte Carlo simulation to be able to find the correlation. This is the image that we are seeing here. We have the dose, distribution of one field. This field is the sum up of many pencil beams covering the target region. And here we are having the signal of the PET. Okay. Well, now I'm gonna talk about charged nuclear fragments. This is the method that I have been working for the last 3 years. This is the method that that we are now conducting a clinical trial. And the clinical trial is called in vivo. In this clinical trial, we focus on head and neck patients, and we are conducting the clinical trial at the Heidelberg Ion Beam Therapy Facility that I mentioned at the very beginning of the presentation, that is located in Heidelberg, Germany. Just for give you some recapping a little about the synchrotrons. This is a map also of the facility in Heidelberg. So we have here the ion beam sources, so where the gas of molecule is. Here you have the prelinear accelerator, so the LINAC. Here we have the ring. And then there are 3 treatment rooms in this facility. 2, which have horizontal beams. And the other one is this gigantic structure that the weight of this structure, that is the gantry, it's, if I remember correctly, hundreds of tons. And it's so heavy because it needs huge magnets to deflect the pencil beam, and then the structure rotates to irradiate the patient at different angles. Prices about how much it could cost a facility like this. 200 euros. This is what I mentioned to you, that synchrotrons have a huge advantage. You can have multiple beams. You can have something that is called mixed beams, in which you have, for instance, carbon with certain energy, and then you have helium, and you can have monitoring of the anatomy of the patient by placing detectors on the other side of the patient and irradiated with very high energetic helium, but then the therapy is with the carbons. So you play around with the range of different ion types to develop monitoring techniques. So the clinical trial, the facility has also an experimental room, and the clinical trial is carried out here in this treatment room. So how our monitoring method works. I will try to make this video work. Okay, it's not working, but this is not a problem. I have it here. So I'm gonna explain to you how our monitoring method works. So here we have, this is called the nozzle, each from where the carbon ions are coming. And there is many sensors here to check the stability of the beam. The white line here is representing the path of the pencil beam. The yellow dots are representing the carbon ions. And when they interact with the nucleus of the atomic nucleus of the human tissue, they can fragment apart. But when they fragment, they tend to go in the same direction of the beam. And we detect the crossing of those fragments, the crossing point of those fragments, using two layers of detector. And then we'll go back to the presentation. Yes, so here. So when the fragment crossed, we record the position where the fragment crossed in our detectors that we call mini trackers. And then in the data processing, we back project the signal into the patient to estimate the fragment, the origin of the fragment. So the red, the pink points now are representing our estimated fragmentation position, and we call those points the reconstructed fragmentation vertices. And if I back project all the fragments that I detect during the irradiation, I can create them a 3D map of the reconstructed fragmentation distributions. And if I compare those maps in between days of the treatment, so if I go and I monitor the patient in different days of the treatment, I can compare these fragmentation distribution vertices. And if I see differences, my idea or the idea of this project is to spot interfractional anatomical changes. So here, this is, now I can introduce you, this is the treatment room at the Heidelberg Ion Therapy Facility. Here, one of our students volunteered to act as a patient. This is the beam nozzle that I mentioned to you. This is some pictures that we took to show the detection system. So this detection system we designed and built. I will explain to you in the next slide. And those are some members. Now, some of them already left, but this is basically the team for the in vivo clinical trial. This is the radio-oncologist, Dr. Semi Harabi. This is the group leader of my research group, Maria Martisikova. And now I'm working with Rebecca, which is a PhD student. And the idea is that we are recruiting patients and study the feasibility of this method in a clinical environment. So about the detectors that we use some detectors that are manufactured by the company that is called Advacam. They are placed in Prague, but the readout was developed at CERN from a collaboration that is called MediPix. The detector has two silicon sensitive layers, and the detector, they are called hybrid pixelated semiconductor detectors. They are hybrid because the sensitive layers and the readout chip are separate, and then they glue them together. And how they glue together in this case is that they put small spheres that they call bonbons, that they merge the silicon layer and the readout chip, and each of the bonbons represent a pixel. So when you buy this sensor chip, looks something like this in a normal plate. So we are using Timepeak-3 chip. This is how it's called. It has a sensitive layer of silicon and a Timepeak-3 chip underneath. It's very small. Each of this chip is just 1.4 plus 1.4 square centimeters. And our detector was customized for our purpose. And what the company did was to put two of those chips in the front and two of those chips here in the back. The pixel resolution of the size of the pixel is just 55 micrometers. and that the data acquisition is performed with a timely resolution of around 1.6 nanoseconds, so we don't miss any particle. So the company Advocam provide us with our customized detectors, and we designed where the detectors will be. So this part of the detection system was built by Advocam, and then we did the rest in our research group. So we built the whole structure with aluminum profiles. This is a sensitive area of our clinical monitoring system, which has 7 of the modules I already mentioned to you. Here in this box, we have a cooling system because our detector needs cooling. And we have a high performance computer for the data acquisition. Something that is important and compared with another monitoring methods is how compact is our monitoring system. And we need just 2 cables to operate. An Ethernet cable that basically gives us access from outside of the access and control to the detectors from outside of the treatment room, and a power cable. Also, we need to make sure that our detection system is always in the same position. And for it, we drill some aluminum profile to the concrete floor of the facility. So what we are seeing here in what color is like green is this raised floor, but underneath we have this aluminum profile that goes directly to the concrete floor. And then we place this cone shape on top, and the negative of this cone shape is in the 2 front legs of our detection system. And with it, we are sure that the detection system is always placed in the same place. So let's go back to our Sears Phantom. I use this example at the beginning to explain you how the dose can be, the dose position can be differed from the planned dose or the delivery dose based on the planned dose with a small anatomical change. So here I have those differences, and this is what we do. So we place our detection system close to the patient, we go outside, the patient is irradiated. At the same time, we are collecting the data of the detectors. In the post-processing, we back project our data. And what you are seeing in these images here are the reconstructed fragmentation vertex distribution for the phantom without the cavity insert, and here with the cavity filled with the silicon. And here, the differences that you are seeing between these 2 distributions is basically the confirmation that our method works. If we are seeing differences in the signal, our goal is to be able to link those differences in the signal with anatomical changes. So I'm working the clinical trial. I joined the group when they were designing the detection system. And my main task was to generate the Monte Carlo simulation for this project. So I designed a workflow, an end-to-end workflow in which they take the patient-specific data. The simulation is performed. I model the detectors in Monte Carlo. I use Fluka for doing so. And the output of this end-to-end pipeline are fragmentation distribution images for the analysis. But in the Monte Carlo, we can also get access to the true origin of the fragmentation. Because if you remember, what we are what we do in our back projection method is to get an estimate point. And why it is an estimate point? Well, because the fragments suffer of multiple column scattering when they are trying to exit the patient. And they can also be stopped or lost their energy when they try to escape from the patient. So in the simulation, we are always getting or scoring the true fragmentation vertices. And here we can correlate in a very clear way the filling of the cavity. And why I know that it's red, I'm gonna explain you now. When there is a cavity filling, so there is more tissue in the follow-up monitoring day, we are always seeing this signature in our fragments. We have less fragments before. We have less fragments before the cavity because the fragments that were created here in the first fraction on the first monitoring day can be then absorbed by the newer tissue. Absorb means stop. Then there is more tissue here now, so the probability that the fragmentation occur increase. And the denser the tissue, the more probability of fragmentation is. And then we have less fragments in this region because the primaries that were coming from this direction now can't interact with the new tissue. So the range is reduced. The primary is supposed to arrive here, but now they are not arriving because they are interacted or getting stopped by new tissue. Some other quantity that I can get from my simulations is something called hadronic inelastic hadronic inelastic interactions, because are basically, among others, all the fragmentations that occur. So all of them, not just the one that we detect. Because these two images that we are seeing here are based on just on the number of fragments that we detect with our very tiny detectors. Okay, any questions until here? I have just 3 slides more, but we are almost there. Questions?
So, questions? Okay.
Okay.
At the end.
Let's continue. So I know that this workshop, in this workshop, the idea is to present new modalities. So what is new? The monitoring methods in particle therapy are new, as the therapy is not new, but because of the price of the machines and how they developed in history, the therapy, the access of the therapy is new and is concentrated just in some parts around the world. So there is particle therapy in Europe, there is particle therapy in Asia, mainly in Japan, some centers in China, and is under construction the first particle therapy facility that is a proton facility. There is also in the US, many proton therapy centers in the US. But there is now under construction the first proton therapy facility in South America, and it's in Buenos Aires. This year, the main conference of particle therapy was in Buenos Aires. So if you are curious about it, check it online. But coming back to the novelty or what is new in particle therapy, I brought for you just 3 topics, one topic per slide. So my idea here is not that you understand what is the topic itself, but you get some feeling for what is new. The first topic is called mini beams. So I show you how we wanted or how we built these homogeneous dose distributions in the target region. So this is, in this case, this is just one pencil beam here. And they want them to make some modulator here and split, let's say, the entrance of the beam in small beams. But it's just one pencil beam. It's just one pencil beam, and they put some material. So just part of the pencil beam is going, but because of the scattering that the particle suffers at the end, at the end of the range, the curvature is complete. And the idea of this therapy is to spare those in the healthy tissue. The second one is called arc proton therapy. This is just so far in protons, because I explained you that we have this gigantic gantry that weight, I don't remember exactly how many tons of, 100 of tons. But this therapy basically is irradiate by angles. Right, one angle, then the machine is moved, irradiate another angle, machine is moved, irradiate. The idea here is to have arc therapy, IBMAT. But it has many it is complex. It's just complex to the QA to the system. Now the arc proton therapy is more popular because there are more compact facilities or more compact machines. If you are interested, check in a machine that is called Proteus 1 for ABA. And here, this is basically how they wanted to combine mini beams with arc therapy. And the other topic that is now under investigation, that is a hot topic now, is upright patient positioning. And upright is not, actually it's not new. They start treating patients actually in the past when they were sick. But the problem is that the CTs were always like down, so for the patient to enter laterally. So now there are two companies designing and building, and two companies that already have facilities in operation. One is called PCure, and the other one is Leo Cancer Care, that they are now conducted clinical trials with the patient positioning the upright. And also you can combine this with moving the patient, so you have arc radiotherapy at the same time without the need to have a gantry moving. So beam is fixed and then you move the patient. And with this, I would like to conclude the presentation. And I know that we don't have so much time left for questions, but let's use these 2 minutes that I have left for questions. Thank you very much.
Thank you, Pamela, for your excellent presentation. Question?
Yeah, hello, Pamela. I'm Sophia Heinrich from Institut Curie. First, I want to thank you for your talk because it was crystal clear, really nice talk. I had a question about mini beams and your detection system. Do you think your detection system would have the spatial resolution to produce the patterns of the mini beam?
Yes. So, as I said, I'm not an expert in the field of mini beams, but if the number of primaries is reduced in pencil beam, which I don't know if it's also done, or is the same number of primaries reaching the target volume. If we get less primaries, and if we get to the point that our statistic is too low, what we could do is to increase the number of detectors in practical terms. Also, with the simulations, we can explore that and yeah, see if there is really a need to get more detectors, or if we could do some like normalization to the maximum for the number of fragments that we are getting, and then but as far as I know, it is possible. I'm not aware now of any technical constraint. And mini beams, my monitoring method works just with heavy light ions, not with protons. Any other question?
Yes, Luis Agullas from the Medical Physics Group here in Bogota.
Sorry, but I cannot hear you very well. Could you speak a little louder?
Luis is from Medical Physics Group here in Bogota. Do you hear me now?
Mm-hmm.
Okay. Well, thanks for your talk. You fill a lot of gaps that I have from this technique. and but you also open a lot of questions. And one of them was, I guess you have a lot of secondary particles, and which also give extra dose to the patient. Well, not extra because you previously calculate them, I guess. But I can imagine that depending on the beam, on the ion that you're using, and on the beam energy, you will have a more precise, let's say, transversal to the beam position. And considering these secondary particles and all these things, so the larger the energy, I would expect you to have a better spatial resolution of the dose deposition. But also you will expect to have more secondary particles and an extra dose. So how can you balance this, or if you have detected this with your device, with your setup?
So my setup just benefit from the fragmentation. Yeah, we take the advantage of the physical process of fragmentation. Regarding the dose, there is always this trade-off of which particle to use that has less angular dose, which can be given by the fragments, no? Because if I hear you correctly, you were also thinking about the scattering associated. So how big the pencil beam get, right? So the lower the energy of the particle and the higher the mass, less scattered suffer. So less big is this spot at the end, right? But the fragmentation make at the end the spot be bigger, right? But this is already accounted by the treatment plan, by the treatment planning system. So the models of fragmentations, let's say, are well defined in some extent, models, because but for sure there are in the optimization, when they do the plan optimization in the treatment planning system, they would prefer to have those beams with certain energy, which have less fragmentation. On the other hand, we wanted them to get robust plans or optimized plans in order to get more fragments if it is needed. But as the fragments are already accounted by the treatment plan, the dose coverage is already robust planned. Yes.
Okay, thank you. And I have another question, very fast.
Yeah, sure.
So I have seen that you, or you at the DKF said, the German Cancer Center, you have recently opened courses for this particle therapy, and so since we have around 66 people online and around 10 here on site, do you think are there possibilities for these students to participate at least in small projects there? Do you
Yes.
know how can you share just 5 minutes or 2 minutes of your experience?
Totally, yeah. Thanks for mentioning. Yeah, so my group at the German Cancer Research Center, that is led by Professor Oliver Jekyll. We have always at least 2 courses during the year. There is always a summer school, and there is always a particle therapy course. Both, as far as I know, are hybrid, so you can attend either online or inside. The particle therapy course is usually, they have both courses have always just an online phase and then a live phase. For both courses, you get a certificate And what else I can tell you? I took the particle therapy course. I highly recommend it. They tried always to make the course accessible for everybody. Means that it's not so pricey. You need to register, send a letter of motivation, if I remember correctly, and I can share with you the link. My experience is both the particle therapy course and the summer schools are worth it. The summer school each year has a different topic. This year, I think, is a little later to register. This year was, I think it's Emma Wright something. I am not very aware of this year course. But we already have students from Colombia participating in those courses. So just give it a try, register, check the webpage, send the documents. As I said, they don't cost that much, and you can follow the course fully online. If you can come, also please take the advantages for the students from the National University, because the Heidelberg University has an agreement with Heidelberg University. So please, I invite you to take the advantage of the agreement to come for internships as well. I know that the funds are very tricky many times, but give it a try. It's worth it. This is how I got here for the first time. I came to do an internship. Then I was accepted to do my master thesis here, and then I applied for the PhD, and I just finished with my PhD. And yeah, if you have any other questions, I can also share my email. I think I made a lot of promotions about the courses.
Question chat. There are one question from the chat. Pamela.
Sorry, I cannot hear you that much.
Pamela, have you heard me?
Yes, yes.
Okay. We have a question from the chat. If
Okay,
more
I'm gonna read it. If more detectors were placed,
yeah, around the patient, would it be possible to obtain something similar to a CT scan?
okay. The answer is not, because there are many reasons why it is not. First, because in a CT scan, you have attenuation of the photons in the tissue, right? The scan, the tube of the CT scan goes around the patient, and the reconstruction is, let's say, from outside to inside. This method could be more similar to a PET in the sense that the signal comes from inside to outside. But it's different also to PET, because in PET you have the coincidence of 90 degrees. So the signal is going exactly, 180 degrees in the opposite direction. And my signal, because of the fragments the primaries are coming and they fragment, they also go in the same direction. The lighter the fragment, the more broader it gets, because it can scatter more. So my image, even if I put a sphere of detectors around the patient, I will get more data in a cone in the front. This information is useful? Yes. That doesn't give us any advantage if we think about, for instance, having an image for the planning. No? If we wanted to have some image that is more equivalent to the physics of particles, and then have the treatment plan system evaluating or design in it, it's better to use helium, for instance, but this is another technique.
Again, Pamela, thank you so much.
Thanks for the invitation, and yeah, feel free to also Google my name, you will find my email. Okay? Good day for you and enjoy the last day of the workshop.
Короче, так. Ну, опять же, ты знаете, что ты просто сказала. Потому что, опять же, я не знаю, когда у меня к тебе пришла, почему она вас не зовет. Опять же, почему она вас не зовет, я не знаю.
Okay, thank you very much for our next presentation. It is a pleasure to introduce you with. Sorry, okay. It is a pleasure to introduce you with Ángela Henao. She's a physics. She holds a degree in physics engineering from National University Campus Colombia. She's a master in medical physics from University of Valencia, and currently she is pursuing his second year of a PhD at the Institute of Microtechnology of Barcelona. And today she's going to talk us about the silicon carbide dosimeters for flash radiotherapy applications. So, Angela, the audience is yours.
Okay, can you hear me and see my screen?
Yes.
Okay. Okay, hello everyone. First of all, I would like to thank to Professor Maria Cristina and her team for all their work with the logistics of this workshop. Besides of the meeting is so important for the scientific community of medical physics in Colombia. So thank you so much also for the invitation. So I am Angela, and today I am going to talk about the topic of my PhD, that is innovative silicon carbide detectors for flash radiotherapy. I am studying in the Centro Nacional de Microelectrónica under the supervision of Consuelo Guardiola and Iván López Paz. So regarding of the Institute of Microelectronics of Barcelona, is located in Barcelona, and it has 270 staff, 70 laboratories, and also it's considered the largest clean room in European Union in the Southwest. And also at the moment, there are 8 research groups that this has a lot of published papers. And then I belong to radiation detector group, that is a general group that develop radiation detectors for several applications. But also I belong in a specific group of this group that is called the BEAM, that is Biophysics and Electronics for Advanced Medicine. This group is led by the Professor Consuelo Guardiola, and we are 4 PhD students and 3 postdoctoral researchers and 2 tertiary researchers. So to talk about more about the clean room is where the devices are fabricated. Some key features about the clean room is that it has 1,500 square meters. It has 190 process equipment, and also it processes 2,000 wafers per year. And this is the ISO class, that is how much cleanness is the clean room, that it has to be super clean in order to fabricate the chips. And also this is the processing area. Just to mention some, one is thermal processes and chemical vapor deposition, metallization, photolithography, ion implantation, nanolithography, electrical characterization, and others. And I am mentioning this, the clean room, because here is where we developed the detector. So I am going to talk with more details in the follow slide. So it's just to, this image is just to show you, if maybe someone didn't know what is a wafer. So wafer is like a disc. And that is that we do all the process of microfabrication, and then when the wafer is ready, we cut in the chips. And then the chips is that we work. So I am going to show a video. Yeah. Okay. To follow with the presentation, the outline of today is to talk about the flash radiotherapy, then talk about the dosimetry in flash radiotherapy, then the silicon carbide detectors, and finish with the open gate simulation. So to start with the flash radiotherapy, so about the beginnings of the radiotherapy, as we know, since the discovery of the X-rays and the radioactivity, various technologies have been developed to destroy tumoral cells using the energy of these particles, and this led to the birth of the radiotherapy. So when we talk about the radiotherapy, we talk about the therapeutic window that is so important in order to give more radiation to the tumor while protecting the healthy tissue. And for that, some different approach in radiotherapy want to widen the therapeutic window. So there is a new modality that started to be considered where we deliver ultra high dose rate. That means high dose radiation in just microseconds. So in 2014, a very important study was done with 240 mice. That it was a study. This mice was split into two groups. One group was irradiated with conventional dose, and the other with greater dose, that is ultra high dose rate. And then was studied the fibrosis of the lung. So they showed that the mice that was irradiated in condition of the flash, I mean with these types of the ultra high dose, the lung was healthy. Though that is was so good because this means that reduce the toxicity up in when was the irradiation. But it was not the only, because also it was so the control tumor. So that is we call the flash effect. So it's the blends of the two effects, the healthy tissue and also the tumoral control. So as we can see in the image, it has been studying different organs in different animals with the different types of the energy. So the majority reporter is electrons and also protons. No, yeah. And X-rays is not too much because it's quite complicated to get ultra-high dose rays for the technologies in X-rays. So, I mean, but there are other projects, but yeah, it's just to say that. In 2017, it was other the study that it was irradiated 96 mice with a dose of 10 grams with different dose rates. And then it was doing a novel object recognition test. The novel recognition test is a special test for the mice where in the first they do a training pass in order to recognize two objects, random objects. And then the mice are irradiated, and then is to do a test in order to push a new object. So theoretical, if the mice didn't have a lot of damage in the brain, he's going to recognize again for the training. But also it is a way to study is to study how much was affected the brains of the mice. So for that, they calculate the RR. So in order to know that if the RR is greater, it's a head to mouth because they recognize again the last object. But if the RR is short, that means that it was a damage to brain. So at the end, the result is well demonstrated that the ultra-high dose rates, I mean the mice that it was irradiated to ultra-high dose rates show an higher RR. For that, it's like it was a healthy mouse in the brain. Different from the results of the mouse that present damage to brain. So this was other studies that had been reported. For example, it was a mini pig that it was irradiated to dose in different, also in conventional and flash with different dose rates. And also it was demonstrated that it was better if they use ultra high dose rates. And also it was other study that is a big story, but at the end it was just some cat that it was irradiated also to ultra high dose rates, and they show also that it was better after the irradiation. And also in 2019, it was the clinical experience, the first in Swiss, with a patient that it was irradiated in two ways, in conventional and in flash radiotherapy. So the patient looks a good response, but it is important to know that it was doing with electrons and it was just in the skin. So for that, it's important to make sure that now is going different randomized trials, with patients with skin cancer, with cutaneous cancer, abdominal and head and neck cancer, but all the studies is in at the moment, there is not like, yeah, we can do flash, yeah, but it's in studying. So for that, it's so important to mention that. So about the biological mechanics, because again, everything as okay, we know that the flash effect is that there is a preservation of the healthy tissue, but what mean, why? So there is one theory that is the most theoretic that is related with the quantity of the oxygenate, like we know if we have a cells, yeah, and we have cells that is well oxygenated, the survival fraction is going to be 50% at 3 grades. And that makes sense because if there is more oxygen, it's going to be more contribution of the free radicals. So, however, if we have one environment of the cell with low oxygen, it's going to be the same survival fraction, but with more dose. And people at the beginning were thinking that in flash radiotherapy, there is a depletion of the oxygen. And for that, if there is depletion of the oxygen, is going to be less oxygen. And for that, the healthy tissue is going to have less oxygen and it's going to be radio resistant. But at the same time, it's not going to pass with the tumoral cells. So that is like the typical theory, but I have to say that it's important to say that there are more theories and it's not resolved yet. So yes. Okay, I'm going to do a sum up. So we have conventional radiotherapy with the average dose rate less to 0.03 grams per second. And we have flash radiotherapy, that is ultra high dose rate. It had been studying from years ago. They stopped because they didn't believe in flash radiotherapy, and also because it was a lot of technologies to do ultra high dose rates. And then it started with the 2014 with the first discovery in vivo, and then in this moment they are studying the possibility to do in clinical translation. Okay, so now we are going to talk about the flash radiotherapy. Okay, so we are talking about a radiotherapy, so now we need to do the dosimetry in this type of the treatment. So we have the passive dosimeters, we have the radiochromic film that it works super well. Sophie Henrich and Sebastian mentioned in the other conference. So it's well, and also it had been using for in vivo experimentals in order to know the dose that is applied to the patients. And then we have other passive detectors, such as alanine, that function well. Alanine is like an amino acid that forms stable free radicals when it's exposed to ionizing radiation. And then this is read out with a process that is called electroparamagnetic resonance spectroscopy. And the response is also so good. It's important to mention that there is other passive detector that has a good response. I'm not mentioned, but for example, thermoluminescence dosimeters and also optically stimulated luminescence, OSL, also works well. So, but what is the problem with types of the dosimetry? Yes, it works well, but we need to know how much dose we are delivering in real time. And also because we want to design some detectors in order to do quality assurance to the beam, that we know that it's so important to know how is the beam at the moments of the therapy. So if we start to talk about the active detector, so we have the ionization chamber, that is the most famous active detectors in radiotherapy. But the problem is in flash condition, as we know, start to be a recombination because it's too much particles in a short time. So at the end, it's possible that if you start to increase the dose per pulse, is going to be no good ion collection efficiency. However, it's important to mention that there is some proposal ongoing that Sebastian talked about that is ultra-thin parallel flat ionization chamber, the UTIC, that works well. And also it has been reported those per pulse greater than 5 gray, the gray per pulse, that this works well. Okay, now there is some other types of the active detectors, like a semiconductor detector. Okay, we know that there is some material that is the conductors and also the insulators, but we have semiconductors that has this actual material has valence band and conduction band. And then if you deliver some energy from ionizing radiation, it's going to generate electron and hole. And also the electron that is generated is current that we can measure. So that is the working principles of the semiconductor detector. And the skills about these detectors compared with the ionizing chamber is the high density, because they have large energy loss in a short distance. That means that we can develop small detectors. Also, the low ionization energy, because they just generate a few electron volts per electron hole pair. Different for the gas detector because the ionization pair is greater. So, and also the well-developed manufacturing technology, and also because the semiconductor detector doesn't need external voltage bias. So we have the diamond detector that, as we know, because it was also mentioned, works super well. Flash diamond was designed, it's a product of the PTW and works well. It has been demonstrated in different studies that at the end, if we measure the dose per pulse, it has to be linearity until 7 dose per pulse, even more, but yes. And also it has a good resolution of the time that also it has been reported. But what is the problem with the flash diamond is that it has a good response, but I mean, it's diamond, it's expensive and it's unusual to get a wafer. The wafer, like I show you. So for that, we have we wanted to propose some new material that is a silicon carbide. So what happened with the silicon carbide? Silicon carbide has to be studied since years ago. It has been investigated as a radiation material and recent renewed attention because of industrial interest in the green energy revolution. So if we start to compare the advantage of the silicon carbide detectors compared with the silicon and diamond silicon, because silicon has been used a lot for a clinical application, and the diamond that we know that exists, the flash diamond, the wide bandgap energy is greater than silicon. So, I mean, obviously it's not so greater like a diamond, but if we compare just with silicon, we can see that it's greater, and that means that it's not affected by the variation of the temperature. It has low leach current, and also it's insensible to visible light. Other thing that I don't mention that, but it's important, is because it has the bandgap is greater. It's possible that if we deliver some value of the doped is not going to saturate like a silicon, because at the end they need more energy to produce electron and hole. So that is also so good. And then there is other feature that is important to mention, that is atomic displacement threshold. That is better, the silicon carbide compared with the silicon. That means that it has high radiation hardness. That is good for the condition of the flash radiotherapy. And also, if we compare the silicon carbide with diamond, we can see that there is a good price to performance ratio. So it's good. So the detectors of the silicon carbide we do in the CNM in the clean room. So we just get the wafers of the silicon carbide with something that is called epitaxial layer of the 3 micrometers. What is epitaxial layer? Is like a special layer that has more crystalline structure. I mean, it's more, it's more poor. It has less defects compared with these parts of the silicon carbide. And also it's possible to control the doping in these types of the epitaxial layer. So I'm going to show here that, So that is good because we have 3 micrometers of the epitaxial, and as you can see, the dope, the levels of the concentration of the dope is different of this type. So that's good because we can control that just the junction part of the sensitive volume is going to be just in this part in 3 micrometers, and that is good because for dope purpose higher is not going to be saturated. Yeah, it's super good. So then about the structures of the silicon carbide diode, so we have here, that is the sensitive volume. This is part of the bulk of the silicon carbide. And then we have these types of the metals, as you can see, from metal 1, from metal 2, and here the metal, because at the end we need to do contacts omics in order to measure the current. So for that we have to add these types of the metals and the passive dielectrics in order to protect the detector for the damaged exterior. So as we can see, this is the wafer, and this is just one diode of 1 millimeter. So this is the way that we fabricate the detectors in a wafer, and then we start to cut, as I show you, in different parts to get the diodes. Okay, so I am going to talk about the first test in flash condition that was made with silicon carbide. That is what made for our laboratory. It was in Germany, in PTV, that's a laboratory of metrology. It was with an electron beam of 20 MeV with a repetition rate of 5 Hz and pulse duration of 0.6 and 1.6 and 2.9 microseconds, and the silicon carbide diode was just measured to 0 voltage. It was not a voltage, external voltage. And it was measured with encapsulation hot made. And it was used the reference dosimetry, alanine, and the flash diamond that I mentioned. So it was period to measure the sharper poops of our detectors for different poops wide. And this has so well because we can see that it was linearity until approximately 10 grays, that is the dose per pulse. So it was well, and also the residuals compared with the fit, it was also super good. It was measured also the PDD in order to compare with the flash diamond. As we can see, it was not too much the deviation compared with the flash diamond, that it wasn't good. And then that is plot is show the relative change response. So we first measure the silicon carbide in normal conditions, and then we irradiate the silicon carbide with 100 kilograde in order to see if maybe it was a loss of sensibility, and not really, because at the end it was the change in the relative change. So that is good because that shows a radiation hardness. So it was super good. And then it was measured again after to do the over-irradiation of the silicon carbide. It was measured again and compare the measure with a microsilicon detector. And as we can see, a microsilicon detector start to be saturated in some dose per pulse that I said for the pictures of the silicon carbide. So the silicon. Okay, so this was the relative change in response. It was some similar to the before, but just changing the temperature because they wanted to see that maybe it was some dependence of the temperature, and really not too much. Okay, so the next I'm going to talk about one of the experiments that it was my first time of my PhD. It was in Alba, here in Barcelona. This is a synchrotron. As it was explained in the last conference, a synchrotron is just to have an electron beam, and they start to be accelerator with a cavity, and then we have a magnet. And then it's possible to generate synchrotron radiation. So we were working with these types of the beam line because we want just to study the detectors with 20 kep. And also these types of the beam has a size of the 5T by 5T micrometer, square micrometer. So that is what's good to have beam small, because we wanted to pass for all the detectors in order to do types of the characterization. So we were working with these different detectors, the silicon carbide with layers of graphene at the top, and also with the metal, and other with not metal. I mean, when we say no metal, it has to be metal, because as I said, it has to be ohmic contact, but it's going to be less metal. So that's that beam. So this is the beam, and then we put the detectors here, and then we start to move in this direction. So that is what the results. So we were mentioned that, as you can see, if we start to compare the response with the silicon carbide with metal and silicon carbide with graphene, we can see that there is a over response in the current that it was measured. And also when we start to study with different energy, also the detector that has more metal start to have more over response. And that is so important for us because when you are developing different detectors, you need to know how much metal to get, or what materials to put in the detectors in order to doesn't have problems then. Okay, so also it was other study that we did in Madrid in the Center of Microanalysis of Materials. It was with a proton beam with 7 MEV, and the pulse width was of the 20 microseconds. It's important to mention that the Center of Microanalysis of Materials is not like a hospital, but we can have proton. That is important. And for that, we have to do the dosimetry that we did with EVT4 and laminated gap chromic, that we have other calibration curve from a hospital. So then we measure with the size of the film, and we compare with the calibration, and then in this way we could calculate the dose. And yeah, that is me with the gap gramming. So then we were measuring the dose linearity with the silicon carbide of 2 millimeters, and we record the charts per pulse. But here it's important to see that we was working with a silicon carbide of 2 millimeters pre-irradiation, but then the silicon carbide was irradiator, over-irradiator, and then he lost sensibility. It was over-irradiator of 52 kilograms. So it was a lot of those, but something that is important to measure here is, I mean, the silicon carbide was over-irradiated, but again, it's possible to use. It's just to, again, to do a calibration, and then it's possible to use that's important to say. I mean, the detector lost sensibility, but it's useful still. And then we were studying the position result with the silicon carbides of 1 millimeter of array. It was a shorter detector, so we use an array of the four detectors, and we start to vary the position. So as you can see, for example, if we see the red and the blue, and this is the green, so you can compare. So we start to move the beam in this way, in order to know if the response was some relevance or some relation with the position, because at the end, our laboratories want to implement a rise of the detectors in order to have more space resolution, and also for flash radiotherapy that we want to achieve. So it was other that it was the time result with the silicon carbide, because we wanted also to reply the measure that I showed about the flash diamond is to measure if the detector has also the resolution of the time. As we can see, I don't know if this is clear, the dark, I mean, is the dark and the clear colors is the difference with white between 5 and 30 microseconds. So it was good because at the end we can see that also it has a good response in the time. So it was well also. So now I am going to talk about OpenGate. OpenGate is the simulation program of Monte Carlo that I use to simulate the silicon carbide detectors, and also to calculate the dose and the energy deposited of the different materials to do Earth beam time. So I recommend you, if someone wants to start to do simulations, because you can to have some different applications such as nuclear imaging, radiotherapy, X-ray imaging, detector dose, and also we had compared with experimental measure, and I think it's good. So that is the work that we are at the moment in ongoing. We were in the Institute Curie because we were testing the silicon carbide detectors, and we also did the measurements, so similar that I exposed to the protons, and I exposed to the measurement that was made in Germany. But in this moment, this result is in processing and in studying, and it's going to be published. So I hope the next year, if I am invited to to present the results. So I'm just going to talk about at the end of my experience in the Institute Curie, because for us it's so important to simulate the silicon carbide detectors to know how much dose they are receiving. But for that also it's so important to simulate the beam of the electron flash in order to know how much energy we are delivering, or the divergence of the beam. So we were in the Institute Curie for my first month of the stay, studying how was the configuration of the beam, doing different measurements. So for example, that is some of the things that I was working with Sebastian in order to simulate the Gaussian distribution with some of the applicators and just Waterbox, and started to graph the PDD and compare with the measurement that Sebastian did with the UTIC and the gap chromic experimental. And also I was simulating with different divergence of the beam in order to see maybe the PDD chain, and that is something that we want to study. So it was made for gap chromic in the PMMA, and also I was simulated with the PMMA in order to also to see how much precise is my simulation compared with the experimental values. Yeah, so also we were studying with these types of the collimator that is special for irradiate mice. And then we were measurement and measurement the PDD and in conventional, also in flash, and doing other experiments. And also that we want to achieve is in order to simulate this collimator and then to simulate the dose, as Sebastian says in the talk, to simulate and to know how much dose they are receiving in order to create a phantom in a future and normalize or characterize these types of the things. So thank you so much, also especially to Professor Sophie Henrich and also to Sebastian and for the group in the Institute Curie. And that's all.
Thank you, Angela, for your excellent presentation. Question from the chat? No questions?
Okay.
Again, Angela, thank you for accepting our invitation.
Thank you.
Okay, now we are going to take 30 minutes to take a coffee break. We Dr. Simone, do you hear me?
Yes, I can hear you perfectly. Do
Thank
you?
you. Yeah, perfect.
Should I start the video?
In 3 minutes, we
Okay.
start. Thank you.
Can I, please?
Sorry?
Can I share the screen just to be sure that is working?
Not yet.
Okay. Please let me know.
Dr. Simon,
Yes,
please share your presentation, please.
yes. It seems that there is a problem.
Do you hear me?
Yes, I shared the screen, but said that something is wrong.
We are
Share.
revising.
And now, can you see?
Yeah. You see.
Okay.
Continue. Dr. Simon Klodowicz is working in the medical physics department at ERD, where she supervises master and doctorate students in diagnostic radiology and radiation protection. She led the diagnostic radiology division at the Instituto de Radioprotección y Dosimetría, ERD. Additionally, Dr. Klodowicz serves as an associate editor and reviewer from the journal Radiation Protection and Dosimetry. She is also a reviewer for applied radiation and isotopes, as well as the Brazilian Journal of Radiation Science. Thank you, Doctor, for accepting our invitation. And this talk is titled Photon Counting CT, una tecnología revolucionaria para el diagnóstico. Thank you.
Thank you. Thank you very much. Good morning, everyone. First of all, I would like to thank the organization of this important event to invite me to give this talk about this revolutionary technology, photon counting CT. As mentioned, my name is Simone Codrulov-Gehenge, and I work in the Institute of Radiation Protection and Dosimetry in the Department of Medical Physics. Before we talk about the PCCT, I would like to remind you about another important technology, DECT, dual energy CT, where we can have image acquisition with two different energy spectra and to enable the differentiation of certain material, mainly calcium and iodine. We know that we have different types of equipment. One of them is the first here in the picture, dual source, where we have a fast KV switching. The second one is a single X-ray tube with alternative energy. As you can see, the double colors, orange and green, just to represent high and low energies. And the third one, which has two layers within the detector. The superficial layer absorbs low energy X-ray photons, and the deep layer absorbs high energy photons. Although it's a very nice and very important technology, we still have some limitations. Requires additional time for processing images and review images. There's a lot of image to review, and for a hospital, it's very important to consider the time consuming. Also, is need a very expertise to do this work. It still has image noise and some challenge in quantify attenuation. Also, we have artifacts, and as I told, require this expertise, so many education and training for the personnel, for the staff of the hospital. So PCCT is emerging technology, and we know that is the future for transforming clinical CT. This technology overcome limitation of conventional X-ray detectors AID. That means the kind of detectors that most of the computers, the conventional computers, tomography equipment has, by employing the direct X-ray. Sorry, something. Overcome limitation convention X-ray detection, and by employing the direct X-ray detection technique. We had the first commercial equipment available in 2021. The manufacturer is Siemens, and currently is the only one, although many others are developing this technology too. So what happened is that this dual source system with this integrated detectors, energy integrated detector arrays, is replaced with a cadmium telluride-based PCD array. And what is the advantage of this? Well, this technique allows adjusting imaging resolution and a number of energy thresholds by combining detector pixels and using different pairings of energy thresholds. Also, we have acquisition modes, different acquisition modes for different application and different needs. Macro chest, ultra high resolution, and sharp modes, each corresponding to a specific detector configuration. We have many advantages in this technology, and we can see better spatial and contrast resolution, lower noise with lower acquisition dose, artifact reduction, optimized use of contrast. As we can see here in this picture, we will talk about each of these properties, and we will see the benefits for the patients. So first, let's talk about the clinical application. It opens much more applications in CT in fields that sometimes we had restriction for some patients or some kind of diagnostics. First, we can see the musculoskeletal imaging. As we can see very well bones and joints, and the detection of soft tissue abnormalities too. And we can detect early stage pathologies. Another significant benefit is in pediatric procedures, because we can do faster exams and then without sedation, and especially with lower dose. That's our concern regarding procedure in patients, in pediatric patients. Another important impact will be in cardiology, where we will be able to visualize some details of small structures, allowing the inclusion of some patients with severe calcification or stents that we could not do it before with the old technology. And as I know that many participants in this event works in radiotherapy, this technology will be very, very useful on oncology. With this low-dose spectrum image, we will have an improved observation of tumor and metastases. Pulmonology. As we know, we will have high resolution. That's really, really important for this kind of procedure. Lower dose in the spectral information. And we have to consider that we will be doing a diagnostic of vulnerable patient with lung disease. So we will have much better information for these patients too. And also, considering the better contrast and the spatial resolution, of course, in neurology, it will be a big benefit because it allows for the evaluation of small anatomical details, even in the smallest cerebral blood vessels. If you search in the literature, you will see many publications regarding this topic because it's really revolutionary in many areas. These are some publications of 2025 publications. Here I just highlight the musculoskeletal radiology and potential benefits for pediatric procedures. And also, I like it to highlight the application in cancer radiotherapy, where you can see that can overcome key challenges in radiotherapy, such as accurate tumor delineation, precise dose calculation, and treatment response monitoring. So this technology will improve anatomic clarity, enhances tumor targeting, while minimize damage to surrounding health tissue. That's the big issue that we want in radiotherapy. The treatment without affect health issues. Another important point is dose and image quality. All the time when we talk about CT, we are concerned to the dose received by the patients. So now with this technology that we will give some details how it works further, we will see that the dose can be reduced even though you improve the image quality. Many studies have demonstrated this, the big potential for radiation dose in many clinical applications. Here is just one example in CCTA, coronary CT angiography, procedure made to evaluate the suspected progression of no coronary artery disease. So here in these arrows, you can see in different thickness, you can see the calcified plaque here in the first one, 0.6 millimeters, 0.4, and 0.2. And here in the inset image, the coronary stenosis. It's obvious in these pictures that when you use the ultra-high resolution 0.2 millimeters, it leads to less calcium blooming, which provide for us more accurate estimation of luminal percentage diameter stenosis on absolute basis and impact classification of patient disease status. Well, I talked about the energy integration detector, AID, but what is that? Well, this energy integrated solid state detector that I told you that most of the conventional CT use this kind of detector. This detector incorporates all the energy of the X-ray photons to form the image. So as you know, in the scintillator layer, you have the incident photons that are converted into light photons and then generating an electrical signal proportional to the total energy deposited during a measurement interval, rather than energy of an individual X-ray photon. And what is the impact of this? This is a limitation because we will not have the spectral lines. This function of X-ray energy from different materials, such as contrast medium or tissues, that will not be able to be captured. And since we know that the electron sign is proportional to the sum of all the photon energy, the signal corresponding to the low energy photons, which carry much of the image contrast information, is weighted downwards, deteriorating the image contrast. Another issue here is the septa or septum that we have between the detectors. This is important and fundamental to avoid that light photons cross between the detector's elements. So we have this partition the different detectors to prevent this effect, that the light photons cross between the elements. However, with this septa, we create a dead area in the detector. And of course, we will have geometric radiation dose inefficiency, especially when we try to build smaller scintillator detector elements. And again, if you try to search about this kind of detectors, you will see that they achieve a fixed size. They cannot do it smaller as they want. So this is a strong limitation, and we will see some effects of this. In the case of semiconductor detectors PCD, the big difference, that is they count incident photons individually and quantify the energy. So we can have spectral information without noise, with noise elimination. So we can have this energy very well quantified, and we will eliminate the influence of the noise. And also, we don't need the septa in this kind of detectors, direct observation of the photons. So the detectors are much smaller than AIDs. This is one reason that we have better spatial resolution. So here we have one list of available system. Sorry, I didn't mention the article of where I took this table, but it's very new, 2025. And here again, we see that Siemens has the FDA cleared in 2021. The other is still have to do some preclinical tests, but they are doing a lot of work to develop different kind of equipment, different types of equipment, different technologies, and always trying to improve this new technology. But nowadays, we can have commercially available only Siemens. So talking about a PCCT, we will see that the X-ray photon is observed in a semiconductor material, generating a positive and negative charge. Under the influence, the application of a strong electric field, these charges are pulled in opposite directions, generating the electrical signal. But you can see this is directly. We don't have anymore the scintillating layer. So it's a very important benefit, this direct conversion to electrical signal. So each registered photon gives rise to electrical pulse whose height is proportional, of course, to the individual photon energy. If you set more than one threshold, the registered photon can be sorted into several energy beams based on the energy ranges. So here we have another representation, measure X-ray spectrum divided into number of energy beams. Another example that we have here is with 4 counters operating at 4 energies, 20, 35, 60, and 75 keV row energy, and are read out simultaneously. So the detector will provide 4 raw data streams containing only counted X-ray quanta with observed energy greater than the respective test row energy, exactly as you can see in this picture here. So why we can eliminate the problem of electronic noise? Well, here for this technology is easy because we know that electronic noise usually is detected as a low amplitude signal. So it can easily exclude of the measured counting data. How? By setting a proper counting energy threshold. This, in the picture, you can see that you establish this threshold in order to be slightly higher than the energy level associated with the energy electronic noise amplitude. Another important advantage is the dose efficiency. PCCT has a constant dose efficiency as a function of count rate. We have an exception for very high count rates where peel-out occurs. We will talk about this later. But for an energy integrated detector, AID, the electronic noise becomes significant at very low count rates, reducing dose efficiency. And what about spatial resolution? Well, in this case, we can have very small detectors, as we can see, 0.11 by 0.11 square millimeters. So we have better spatial resolution. We will see, however, that we will have the limitation for that. That will be the charge, sharing, and pulse piled up can decrease the dose efficiency and compromise energetic information. This is one issue that we know that manufacturers should treat very careful to improve even more this technology. But anyway, here we can see dose and noise reduction. Look the upper picture here. We did very similar acquisitions with the window level, the reconstruction, everything is made the same. But here in the upper picture, we have the same dose for both procedures. However, you can see that in AID, we have higher noise than with PCD. So here we have same dose, however, look the dose. For AID to keep the same noise level, the dose is 35 higher than PCD. So we have less dose and even we can have the same noise level using this technology. Another important thing that we know the importance of noise reduction to identify some parts, some structures in the body in different procedures. Noise, of course, doesn't allow us to observe some structures because it's mixed in the background. So here we have the conventional, and here we have with PCD. And here we can see clearly that here we cannot identify well what is happening, but here we can see better the caudus healing because the noise will expressive lower than with the conventional. Again, we have here the problem that you know well, that is big hardening artifact. This is a problem in all procedures made with CT. But here we can have a reduction of this kind of artifacts with the high energy beam. You can see both reconstruction, sagittal reconstruction, and coronal reconstruction with low, high, and total energy. It's very important to see that with high energy here, we can see better the structures and avoid these important artifacts that we can see here in low energy. Of course, when we talk about photon counting CT, one important characteristic is the property to do the decomposition of material resulting in energy selective images. So here we can see the energy selective images from 40 keV to 130 kevs. How we do this? As I told you before, we generate from the number of registered counts in each energy bin. So from these energy selective images, we will set of material concentration maps, that is very important for us, that is generated through a data processing method, namely material decomposition. These material concentration maps can be combined in different ways to form the final image, depending on the necessity, the needs of the radiologist, or the kind of procedure or what we want to see. So this image can be, for example, a color-coded map showing different materials, a virtual monochromatic images, or a virtual non-contrast images. So here, the final image, you can see with colors identifying iodine water, and calcium. So we can use different contrast agents in the procedure. Here again, we can see image of multi-K materials. Here in picture A, grayscale image, it was reconstructed from all photons detected, regardless of the detected energy. So, at the level of left pelvis demonstrates the dense contrast material in calibration views, abdominal aorta, and kidney. However, no differentiation is possible between the different contrast agents with a single energy CT. When we go here with the multi-material map, enables this differentiation between iodine, gadolinium, and bismuth contrast agents. So we can have different contrast agents and clearly identify them in different ways. As I told you, at this point, we cannot say that is a perfect equipment because some limitation we still face. One of them I mentioned before is a charge sharing effect. This effect happens when the photon is counted by two adjacent pixels due to signal diffusion across adjacent detector elements. So simultaneous interactions record lower energy, degrading both spatial and energy resolution. Another important effect is Compton scattering. This effect is when secondary photons produced in the semiconductor material are recorded by the same or an adjacent pixel as two separate events, resulting on what? In underestimating the true energy value. And K-escape effect, when a new charge cloud is generated by the K-X-ray fluorescence of the sensor material, and one pixel detects it as two separate events. Here we can see the representation of some of these effects. So part of the photon's energy is deposited in the detector where it strikes. However, the remaining energy is carried by a fluorescence photon, which generates charge in another random location, probably in another detector element. And it's the same case of the K-Compton effect. The result is the same. And the other effects that I talked about is when an incident X-ray photon is observed exactly at the boundary between two detector elements. In this case, part of the generated charge is recorded on each of them. So both effects can cause some of the photon's energy to be recorded on the wrong detector element, which will result in the not high image quality, compromising the quality of the image or degrading image quality. So the pile-up effect occurs when two consecutive photons are counted simultaneously, resulting in missed counts and an incorrect energy report. This kind of effect is always present and depends on what? The count rates, if it's very high, rates, and also depend on the dead time of the detector. And this effect will result in a distortion in the measured energy of individual events, affects the accuracy of energy assessment and the ability to differentiate materials. That's exactly what we want with this technology. To have this accuracy of energy assessment and also the ability to differentiate materials. Conclusions, sorry, it's in Spanish yet. The introduction of PCCT into clinical practice has opened a new area in medical imaging. No doubt about that. The improvement in image quality is already being demonstrated in numerous applications, in numerous clinical applications, especially those requiring higher spatial resolution, contrast, and low radiation dose. This technology also expands their capability of spectroscopy for various applications that have not yet been exploited, especially with the development of KH color contrast agents. So this technical advance also promise to reduce it in a radiation dose in CT at least 30 or 4%. So it's a very important benefit. You keep the image quality or improve image quality, and at the same time, you reduce the radiation dose for the patients. So it's expected that PCCT provides considerable benefits in the diagnostic, characterization, and staging of disease, and to enable new approach not previously possible with the conventional CT. However, PCCT systems are still scarce and open to technical developments that facilitate the adoption of this technology. Of course, should overcome some limitation that we talked about. Even with this limitation that I cited here, all the studies confirm that this technology, even with these limitations, will be very useful and very important for the diagnostic, for the improvement of the diagnostic. But as we see, many manufacturers are working on this, and we will see, hopefully, new advances in this technology. So, summarizing, PCCT is an emerging technology with the potential to dramatically transform clinical CT. PCCT can reduce dose, improve spatial resolution, correct beam hardening artifacts, optimize contrast agents, create opportunity for quantitative image, enable the use of multiple contrast agents. I didn't see it here, but they also said that probably we will avoid multi-phase procedures. One phase will be with this technology enough. So here is a table with the potential benefit and clinical application. I will not read all of them because most of them we already talked about, but just to see the impact that we will have soon, I hope. In the United States, we already have this technology, but not in many countries yet. I would like to finalize this presentation with a special thanks to Dr. Mahesh for his crucial collaboration in this presentation, providing me many technical materials to prepare this webinar. Thank you very much.
Thank you so much, Dr. Simon, for your excellent talk. Questions?
Thank you, Simone, for your talk. Is Andrea Abril here? Simone, is there any protocol or document to ensure the quality of the image already? Or in case not, which are the steps that medical physicists we have to do in order to have it?
Well, I saw some protocols from Siemens, but probably it's something that will be developed in each hospital. We have some indication, but I didn't find many publications regarding this. I saw much more regarding the benefits, the kind of detectors, demonstrating the dose reduction, but not specifically telling what kind of protocols we have to apply. You see, that's a very new technology, and I think that we still have much to do. But in some, yes, but sorry, just to complete, but some specific procedure we can find some indication, but I will not say that it's a protocol. We have indication from in some publication like musculoskeletal and cardiology, but I will not call this a protocol.
Thank you, Doctor. We don't have questions from the chat. Again, we thank you very much for your contribution in the workshop.
No, it was my pleasure. Thank you for all my friends, and especially for my Colombian friends, that I have a very long story, and that I like very much. Thank you all.
Obrigado. We are wait 15 minutes to continue with the following talk. And at 12 o'clock, we continue. Thank you.
Okay, hello everyone. We are going to follow with the next presentation. This talk will be led by Julian Niño, who is a physicist from National University, and currently he serves as the head of the secondary standard dosimetry laboratory at Servicio Geológico Colombiano, and Camilo Ernesto Calderón, who is a physicist with a master's degree and is currently pursuing a PhD in physical science at Universidad Nacional de Colombia. And since 2014, he has been part of the research group of radioactive applications and at Servicio Geológico Colombiano. So please, the audience is yours. Thank you.
Muy buenos días. En nombre del Servicio Geológico Colombiano, Dirección de Asuntos Nucleares, les agradecemos mucho esta invitación. El día de hoy venimos a hacer una pequeña reseña de lo que ha sido el laboratorio secundario de calibración dosimétrica del Servicio Geológico Colombiano. Este laboratorio tiene como misión proveer la trazabilidad en todo lo que tiene que ver con radiaciones ionizantes. Es decir, nosotros somos los responsables de garantizar que en el país todas las mediciones de radiaciones ionizantes en diferentes ámbitos, como son principalmente la medicina, la industria y la academia, pues sean coherentes entre sí para garantizar que los procedimientos que derivan de estas mediciones tengan los mejores resultados. Entonces, la charla la vamos a dividir en 7 temas principalmente. En el primero vamos a mostrarles un pequeño resumen de lo que es el Organismo Internacional de Energía Atómica. Luego veremos de qué se trata uno de los proyectos, de los recientes proyectos que tuvo el laboratorio, que cerró hace algunos años, con los cuales pues obtuvo parte de su fortalecimiento. En tercer punto, vamos a hablar un poquito acerca del proceso de acreditación que ha tenido el laboratorio, que esto es para garantizar pues la confiabilidad de los resultados. Luego miraremos lo que ha sido la implementación del servicio de calibración a nivel de radioterapia. Vale la pena aclarar que no es un servicio totalmente nuevo en el país, es decir, ya se prestaba anteriormente este servicio, pero estuvo en suspensión por poco más de una década, pues tuvimos que retomarlo de la mano del Organismo Internacional de Energía Atómica hace más o menos unos 3 años. Luego hablaremos un poco ya de la proyección que tiene el laboratorio, incluyendo proyectos nuevos que estamos desarrollando en conjunto con el Instituto Nacional de Metrología y el Organismo Internacional de Energía Atómica, los servicios que estamos desarrollando, y el compañero Camilo Calderón va a hablar también acerca de la línea de investigación. Entonces, inicialmente tenemos el Organismo Internacional de Energía Atómica. Bueno, en primera instancia, pues bueno, el Organismo Internacional de Energía Atómica de pronto ha cobrado un poquito de relevancia en los medios en estos días, pues a razón de algunos eventos internacionales de los que ya nos hemos enterado todos. Principalmente, pues este organismo tiene una función muy importante, que es la de garantizar el uso pacífico de las tecnologías nucleares. Colombia es firmante de los acuerdos que lo obligan a cumplir estas directrices y en algunos casos recomendaciones del organismo, pues para estar en línea con este uso pacífico. Hay un programa que se llama Programa de Cooperación Técnica, a través del cual el organismo, el anterior, bueno, a través del cual el organismo provee mejoras tecnológicas a los países, ayuda mediante proyectos a su desarrollo tecnológico en función pues del uso pacífico de las tecnologías nucleares, y también ayuda a mejorar la parte de la protección radiológica, principalmente a través de ayudas de tipo legislativa, es decir, interactuando muchísimo con los organismos reguladores. Siguiente, por favor. Listo. Esta es la página del programa de cooperación técnica, digamos que es como la puerta a través de la cual se inicia toda esta interacción. Vale la pena aclarar que en el país, bueno, en cada país, existe una oficina nacional de enlace. En el caso de Colombia es el Ministerio de Minas y Energía. Como parte de toda esta estructura que está formada por el Organismo Internacional de Energía Atómica, existe una red de laboratorios que se llama Red de Laboratorios de Calibración Dosimétrica. Esta red pues, fue formada inicialmente, no sé, más o menos unos 40 años, con el objetivo de garantizar la homogeneidad de las mediciones, principalmente en el área de radioterapia, inicialmente. Actualmente pues ya esto se extiende a diferentes áreas, incluyendo la parte de rayos X, braquioterapia, medicina nuclear y la parte de protección radiológica. La idea de garantizar esta homogeneidad de las mediciones es precisamente que todos los resultados que se obtienen de las investigaciones y que luego son aplicados en los procedimientos médicos sean coherentes. Es decir, que una medición que se realice en Colombia sea exactamente igual o por lo menos, bueno, equivalente a cualquier medición que se haga alrededor del mundo. Esto es lo que le da sentido realmente a esos resultados estadísticos y a esos procesos, digamos, de gestión de calidad, etcétera, que se utilizan para mejorar las probabilidades de éxito de estos tratamientos. El laboratorio secundario de calibración dosimétrica hace parte de esta red y obtiene su trazabilidad a partir de allí. En este esquema lo que podemos ver es una estructura de cómo esa trazabilidad se obtiene, se disemina en todo el mundo. El BIPM es la Oficina Internacional de Pesas y Medidas. Los que dice PSL son los laboratorios primarios, es decir, los cuales desarrollan las magnitudes a partir de su definición. Entre ellos se intercomparan y esos valores de referencia internacional se obtienen de esas intercomparaciones de esos laboratorios coordinados por el BIPM. Como parte, digamos, fundamental de esta red está el laboratorio de dosimetría del Organismo Internacional de Energía Atómica, que es el que vemos acá. Y como parte ya, digamos, la parte que aterriza ya todos estos resultados en cada país es la de los laboratorios secundarios, en este caso son los SSDL, parte de lo que somos nosotros. Nosotros somos ya los encargados de dar esa trazabilidad a los usuarios finales. Bien, en el marco de este programa de cooperación técnica, el Servicio Geológico Colombiano y particularmente el laboratorio ha estado suscrito a diferentes proyectos. Uno de los últimos es el COL 0014. Se formuló en el año 2014 y se ejecutó en años posteriores. Hasta hace poco, digamos, se tuvo el cierre. Y fue uno de los proyectos, digamos así, más exitosos que hemos tenido pues, digamos, en términos de los beneficios que ha obtenido el país. Hemos tenido fortalecimiento, digamos, principalmente el haber recuperado el servicio de calibración a nivel de radio alto 60 y la instrumentación necesaria como de los patrones de referencia, además de instrumentación auxiliar pues de un nivel bastante alto. También fortalecimos también la parte de protección radiológica, la capacitación del personal con ayuda del organismo y adicional a esto, iniciamos el proceso de acreditación, digamos unas etapas iniciales antes del proceso de acreditación, que fueron auditorías realizadas por el organismo en función de la norma ISO 17025, que es la que se utiliza para la parte de la acreditación. Son algunas imágenes de los instrumentos que obtuvimos. Lo que ven acá es una cámara de ionización para radioterapia. Posiblemente muchos de ustedes ya estén familiarizados con este tipo de equipos. Este es calibrado en el Organismo Internacional de Energía Atómica. Y lo que se ve acá es un fantoma, un maniquí de agua, muy similar al que se utiliza en las clínicas, pero digamos que con una precisión un poco mayor y es para haces horizontales, además de esto. Aquí lo que vemos es un esquema de cómo esa trazabilidad se transmite desde los laboratorios primarios a los secundarios y luego a los usuarios. Esta instrumentación de acá es la que se obtuvo en el marco de este proyecto, se fortaleció. Acá ya es una imagen pues ya del laboratorio, un equipo que está en proceso de calibración, fuente de radiación, y al fondo tenemos un irradiador de rayos X que se utiliza también con fines de calibración y que fue parte también de las adquisiciones que se tuvieron con este proyecto. Posterior entonces a este fortalecimiento, iniciamos el proceso de acreditación. Esto se hace con el órgano acreditador, en este caso la ONAC en Colombia. Vale la pena aclarar que el proceso de acreditación no es algo obligatorio, sobre todo para este tipo de laboratorios que, digamos, tienen una interacción fuerte con redes internacionales. Es más un proceso de mejora continua que a lo que tiende realmente es a garantizar la confiabilidad de las mediciones. Actualmente nosotros tenemos la acreditación en el área de radioprotección. Estamos vigentes, la obtuvimos en 2019. Y en este momento pues está vigente hasta 2027. Posterior a eso procederemos a hacer la renovación correspondiente. Las magnitudes en las cuales estamos acreditados para radioprotección son la dosis equivalente ambiental, dosis equivalente personal a 2 profundidades, y los otros 3 son para laboratorios, para calibrar patrones de laboratorio. Esto lo hicimos como, digamos, un paso adelantándonos un poco a las necesidades del país entendiendo que para ese momento habían intenciones de algunas empresas privadas de formar laboratorios de calibración. Actualmente ya, perdón, ya hay algunos laboratorios habilitados y nosotros le hacemos la calibración a los patrones de estos laboratorios. Esto tiene dos ventajas. Uno, extender la capacidad que tiene el país para prestar estos servicios. Y segundo, bajar un poco la congestión que el laboratorio normalmente tiene, pues porque hasta hace algunos años era el único que prestaba este servicio. En cuanto a la calibración a nivel de radioterapia, les contaba que con este proyecto se fortaleció la parte instrumental, empezando por el irradiador. Este es un esquema del montaje experimental que se realiza. Es muy similar, digamos, en contexto a lo que se realiza en clínica con un fantoma, solo que en clínica lo que se hace es que el acelerador proyecta las de forma vertical hacia abajo y el maniquí, el fantoma, digamos, se posiciona de tal forma que se hace pues el barrido con las cámaras de ionización en ese haz vertical. En este caso, lo que se tiene es un irradiador horizontal, o sea, viene acá, y es una fuente de cobalto 60. Esto pues tiene relación con la historia de lo que ha sido realmente la radioterapia, en función de que anteriormente no se hacía con acelerador, sino con fuentes de cobalto. Por eso ese fue el estándar internacional y por eso sigue siendo a nivel de laboratorio el estándar internacional, por su historia y por la estabilidad que, digamos que de forma nativa, pues tiene una fuente de cobalto comparado, digamos, con un acelerador. El fantoma se posiciona a una distancia de tal forma que la fuente esté a 1 metro de distancia de la cámara de ionización, a una profundidad de 5 centímetros. Esto es un esquema muy general, pero detrás de todo esto hay un montaje que exige pues una precisión al orden de micrómetros en muchos casos. Esto para obtener incertidumbres que estén, pues digamos, en función de lo que se requiere para los estándares internacionales. En este caso estamos alrededor de 1.2%. Como parte de esta implementación, pues ya digamos el laboratorio pudo acceder también a programas, a proyectos de carácter regional. Vale la pena aclarar que en el marco de la cooperación técnica no solamente se tienen proyectos nacionales, sino también proyectos regionales. Y en función de esto, nosotros fuimos el año pasado anfitriones de un curso de entrenamiento para calibración y medición en clínica a nivel de radioterapia externa y de braquiterapia. Esto se hizo en colaboración con el Instituto Nacional de Cancerología y obviamente con el programa de cooperación técnica del Organismo Internacional de Energía Atómica. Tuvimos la participación de expertos internacionales, incluyendo pues personal científico de acá de Colombia, de la región, el Ministerio de Minas y Energía y del del laboratorio del Organismo Internacional de Energía Atómica. Estas son algunas imágenes de las prácticas que tuvimos en el Instituto Nacional de Cancerología, y esto pues ya fue en el servicio geológico. Bueno, ¿qué viene ahora a futuro para el laboratorio y para el país? En el marco de la cooperación técnica, digamos que los proyectos que se reciben, se hace una convocatoria cada 2 años. En la convocatoria para los proyectos a iniciar en 2026, nos reunimos con el Instituto Nacional de Metrología y planteamos un proyecto. Este proyecto ya fue aceptado a nivel nacional y se encuentran ya instancias internacionales, es decir, con el Organismo Internacional de Energía Atómica, definiendo algunos aspectos un poco más logísticos y de presupuesto, pero esperamos iniciarlo el próximo año. Este proyecto pues está diseñado principalmente metrológica y a la final lo que queremos es esto, mejorar la seguridad radiológica y los resultados de los tratamientos clínicos. Entonces, hubo 3 dificultades que nosotros identificamos en el país. Hay muchísimas más, pero la idea es que estas se van atacando pues progresivamente. Las 3 principales, la primera, no hay acá en el país un laboratorio que calibre electrómetros de uso clínico. ¿Qué sucede? Que en clínica se utilizan los electrómetros y cámaras de ionización. Muchas veces una clínica tiene 1 o 2 electrómetros. Muchas veces solamente tiene 1. La calibración se realiza en conjunto, es decir, el electrómetro con la cámara de ionización. ¿Y qué sucede si el electrómetro por alguna razón se ve afectado se daña, se pierde cualquier situación que comprometa su trazabilidad, todas las cámaras de ionización que están asociadas a ese electrómetro inmediatamente pierden la trazabilidad y hay que volver a calibrar todo el sistema. Si existe una calibración independiente del electrómetro, al perder el electrómetro se puede reemplazar por otro, calibrarlo e inmediatamente se recupera esa trazabilidad. Y también, pues para los procesos de envío de los equipos a calibración, si se tiene que enviar siempre el electrómetro, pues es un riesgo adicional que no tiene por qué ser así. Entonces, lo que planteamos con el Instituto Nacional de Metrología para solucionar esto es establecer ese servicio en el país. Esto va a brindar pues un poco de flexibilidad también a las clínicas. Lo siguiente que nosotros hemos identificado en la constante interacción con nuestros usuarios es el déficit en aplicación de procedimientos de confirmación metrológica. ¿Esto de qué se trata? A grandes rasgos, un equipo que se calibra cada 2 años, digámoslo así como en la parte de radioterapia. En ese transcurso entre calibración y calibración se le deben aplicar algunos procedimientos para garantizar que permanece estable, que esa calibración aún tiene sentido. Eso es lo que se conoce como confirmación metrológica. Y sobre esto hay vacíos enormes en el país, no solamente a nivel de medicina, sino en sobre todo en la parte de protección radiológica. Y finalmente, había hace un tiempo una iniciativa de realizar un programa de ensayos de aptitud. Esto realmente lo que se refiere es ese programa que hace el Organismo Internacional de Energía Atómica con las clínicas de enviarles dosímetros para que los irradien y se evalúa cómo se está realizando la medición en clínica. Digamos, es un paso muy importante, no solamente tener los equipos calibrados, sino verificar que al final esas mediciones, esa irradiación que se le hace a los pacientes, va con las dosis adecuadas, cumpliendo los estándares internacionales. Eso lo hace el Organismo Internacional de Energía Atómica. Aquí en el país, hasta hace unos años, el Instituto Nacional de Cancerología recibía los dosímetros y los distribuía en diferentes clínicas. Es algo totalmente voluntario, pero esto realmente dejó de hacerse hace ya bastantes años. Hubo una iniciativa, como les decía, para hacerlo a nivel local hace unos años, pero por alguna razón, pues, se suspendió esa iniciativa. Lo que hicimos fue realmente retomarla. Es decir, dijimos, bueno, el Instituto Nacional de Metrología tiene toda la autoridad para hacer intercomparaciones. Nosotros tenemos el brazo técnico, unámonos, miremos con el Organismo Internacional de Energía Atómica cómo montamos esto, qué instrumentación adicional se necesita y hagámoslo. Y pues para eso ya hemos obtenido el respaldo del organismo para empezar a hacerlo. Estimamos que lo estemos haciendo más o menos en unos 3 años iniciando. Entonces los 3 objetivos, los productos que les mencionaba hace un momento, ese servicio de calibración de electrómetros para la parte de confirmación metrológica, lo que nosotros planteamos es primero hacer algunas actividades, digamos, de socialización con el país para darle relevancia realmente a este tema de confirmación metrológica. Y posteriormente estaremos haciendo la redacción y publicación de unas guías que sirvan de apoyo a las entidades que deseen aplicar esos procedimientos de confirmación metrológica. Y muchas veces lo que sucede no es que no quieran hacerlo, sino que no existe una documentación aterrizada a este tema que puedan utilizar de guía. Entonces, esa es parte de la iniciativa. Y finalmente la parte de los ensayos de aptitud, de las intercomparaciones con las clínicas. Ya entrando un poco también en los servicios que tenemos en desarrollo, entonces tenemos la parte de la calibración de instrumentos a nivel de braquiterapia. Ya sabemos que la práctica de braquiterapia, en esta práctica lo que se hace también es radioterapia desde adentro básicamente, donde el paciente se le pone un catéter y a través de ese catéter va la fuente radioactiva cerca al tumor. Esto se hace para algunos tipos de tumores en los cuales no es recomendable la radioterapia externa. Para este tipo de prácticas, el instrumento de referencia que se utiliza es una cámara de pozo. No hay pues digamos, un servicio de calibración de estos instrumentos actualmente. Nosotros ya compramos el patrón, ya estamos desarrollando la metodología. Este año tenemos programado hacer la intercomparación con el Organismo Internacional de Energía Atómica, todos los procesos de validación y esperamos estar abriendo este servicio en un plazo de más o menos un año. O sea, esperamos abrir este servicio el próximo año, más o menos por esta época. Otro de los servicios, esto sí es realmente un espectro de servicios, aparte de rayos X, porque esto se utiliza en bastantes campos en la medicina. Es otro de los de los servicios que estamos implementando actualmente y esperamos irlo abriendo progresivamente diferentes ámbitos alrededor de estos 5 años más o menos. Para esta parte y lo que sigue, ya le doy acá la palabra a mi compañero Camilo Calderón. Muchas gracias.
Gracias. Bien, entonces, como hemos visto, el laboratorio está mirando pues un espectro grande de servicios. La idea es abarcar la mayoría de aplicaciones de las radiaciones ionizantes, todo esto a nivel de metrología. En el país no se tiene la trazabilidad o el esquema de trazabilidad metrológica para lo que es radiodiagnóstico ni tomografía computarizada. En ese sentido, entonces, y con ayuda del proyecto que ya Julián ha presentado, del COL 014 con el Organismo Internacional de la Energía Atómica, pudimos adquirir un irradiador, un X80 de Hopewell Designs. Este irradiador pues es diseñado para un tubo que ya teníamos, un tubo de rayos X de 320 kilovoltios, el cual entonces nuestro deber es caracterizar, es decir, de alguna forma empezar a conocer el espectro de rayos X. Para eso, entonces, utilizamos la técnica de los HBL, de la primera capa hemireductora, segunda capa hemireductora, con la idea de implementar unas calidades que están normadas, unas calidades de radiación que están dirigidas precisamente a tener campos de referencia en radiodiagnóstico y en tomografía computarizada. Para eso entonces tenemos también unos patrones. Esta es una cámara típica plano-paralela que se utiliza en radiodiagnóstico, la cual nos ha servido como patrón de referencia. El esquema de trazabilidad es el que se mostró anteriormente, en el cual nosotros esta cámara la calibramos ante el laboratorio del Organismo Internacional de la Energía Atómica y este a su vez tiene una calibración ante el BIPM. De ahí es donde vamos a diseminar entonces las unidades del sistema internacional en base a las magnitudes que se utilizan en radiodiagnóstico, que en este caso es Kerman aire. Y también estamos trabajando en el protocolo de calibración para tomografía. Entonces, vamos a tener calibración a nivel de radiodiagnóstico, es decir, de los sistemas dosimétricos que se utilizan para el control de calidad de los tubos de rayos X en clínica. Vamos a tener radiodiagnóstico, calidades de radiación en radiodiagnóstico, los RQR, bajo el protocolo, obviamente, del Organismo Internacional de la Energía Atómica, y también estamos trabajando para las cámaras tipo lápiz que se utilizan en tomografía computarizada. En esto pues ya llevamos varios años, ya tenemos implementadas varias calidades en RQR y estamos próximos a empezar la caracterización dosimétrica, es decir, vamos a tener varias tasas de Kerma en aire, con lo cual tendríamos las referencias para calibrar las cámaras de los usuarios. En braquiterapia, entonces también estamos trabajando en la implementación para la calibración de cámaras de pozo a nivel de braquiterapia. Como nos mencionaba Julián, a finales del año pasado fuimos sede de un curso regional en calibración en braquiterapia, esto también a nivel clínico, no solamente a nivel de laboratorios secundarios, en el cual se está o se actualizó, de hecho, ya el código para calibración y dosimetría en braquiterapia. De hecho, ya hace algunos meses ya código para braquiterapia, y allí entonces tuvimos la visita de varios expertos, tanto en dosimetría clínica como de referencia a nivel de radioterapia. Estamos trabajando en un convenio con el Instituto Nacional de Cancerología. La idea es que podamos validar el método, un método que ya tenemos establecido, basado obviamente en la normativa internacional, para la calibración de este tipo de cámaras de pozo a nivel nacional. Una vez tengamos entonces el convenio, pues podemos validar con las fuentes de braquiterapia que tiene el Instituto Nacional de Metrología. Y podemos entonces poner el servicio ya a los usuarios en Colombia. Bien, y además entonces de prestar servicios de calibración y de estar incursionando a las intercomparaciones o a los ensayos de actitud que nos mencionaba Julián, otra de las misiones del laboratorio secundario de calibración dosimétrica es también la parte investigativa. No solamente como misionalidad de la entidad, somos adscritos al Servicio Geológico Colombiano, que es un instituto de ciencia y tecnología, sino que también el laboratorio hace parte de una red de laboratorios a nivel mundial y como misión también está fomentar los proyectos de investigación que tienen que ver con la metrología de radiaciones ionizantes y sus aplicaciones. La Dirección de Asuntos Nucleares tiene un grupo de investigación. Atrás. No, allá. La Dirección de Asuntos Nucleares, bueno, el Servicio Geológico tiene varias direcciones. De hecho, si ustedes ven, es algo atípico que algo relacionado con asuntos nucleares, con protección radiológica y demás, esté en un servicio geológico colombiano. De hecho, a nivel mundial siempre nos mencionan que esto es muy atípico, ¿no? Que un servicio geológico tenga esto, pero pues por condiciones que pasaron antiguamente, el servicio geológico tuvo que hacerse cargo de todo lo que tiene que ver con la Dirección de Asuntos Nucleares. Allí entonces se creó un grupo de investigación que se llama Grupo de Investigación y Aplicaciones Nucleares. Esto fue creado en 2017 y recibió el reconocimiento del Ministerio de Ciencias como categoría C. Y en la última convocatoria, que fue la convocatoria de 2024, el grupo ya fue categorizado en A. Ya subimos a la categoría A y tiene varias líneas de investigación, se las voy a mostrar acá. En primer lugar, se creó todo un comité científico en la Dirección de Asuntos Nucleares, en cabeza del director de Asuntos Nucleares, y paralelamente se creó el grupo de investigación. Ese grupo de investigación es liderado por la doctora Mariluz Peña, colíder David Alonso, y tiene varias líneas de investigación. Una de ellas es aplicaciones nucleares y radiactivas para seguridad alimentaria y salud, aplicaciones nucleares y radiactivas en geocronología y geoquímica, aplicaciones nucleares y radiactivas para estudios ambientales y cambio climático. Hay una línea muy específica para reactores nucleares y aplicaciones en neutrónica. Y nosotros, el laboratorio secundario, hace parte de la línea que se llama protección radiológica y metrología de las radiaciones ionizantes. También hay otra línea que son aplicaciones nucleares reactivas para ciencias forenses y patrimonio. Como ustedes ven, esto está muy atado, de hecho, con el plan de desarrollo y los ítems claves en los cuales debería apuntar la investigación. Nosotros pues estamos bajo la línea de salud pública, obviamente, es protección radiológica y metrología de radiaciones ionizantes. En ese sentido, entonces, esta línea pues tiene unos objetivos. Los objetivos son fortalecer las capacidades metrológicas del laboratorio secundario de calibración dosimétrica. Esto lo hemos podido hacer mediante la integración de la simulación Monte Carlo y bajo los montajes experimentales, bajo la dosimetría que podemos medir. Validamos nuestras simulaciones Monte Carlo. La idea es poder fortalecer, por ejemplo, las capacidades de medición, las incertidumbres tan bajas posibles como se pueda. Entonces utilizamos la simulación Monte Carlo. También trabajamos en caracterizar diferentes materiales que tienen algún tipo de interés y caracterizarlos a nivel dosimétrico o cómo es la respuesta a la radiación ionizante. Actualmente pues trabajamos como en la caracterización de algunos polímeros para diferentes aplicaciones. Entre ellos, la idea es que se puedan construir diferentes fantomas o se pueda incursionar en el estudio de las tasas de degradación de polímeros. La radiación ionizante, pues, es uno de los métodos que se puede utilizar para cambiar o modificar algunos componentes poliméricos de algunos materiales que pueden servir para reciclar y demás. También, y una de las cosas que más hemos hecho en los últimos años, es apoyar iniciativas de investigación existentes. Hemos estado muy unidos con la academia, con la Universidad Nacional, con la Universidad Distrital, con la Pontificia Universidad Javeriana, haciendo pues algunos proyectos de investigación o apoyando algunas iniciativas de investigación. Entre ellos tenemos, por ejemplo, caracterización dosimétrica de materiales PLA y PETG para impresión 3D como equivalente a tejido para uso en radiodiagnóstico. Entonces, lo que hicimos acá fue caracterizar cómo es la respuesta, sobre todo la atenuación a la radiación X de baja energía entre 30 kiloelectronvoltios a 70 kiloelectronvoltios, ácido poliláctico y de PETG. Estos materiales son los que se utilizan comúnmente para la impresión 3D y queríamos ver cómo es la respuesta a la radiación ionizante, sobre todo a rayos X, frente al PMMA. El PMMA es muy utilizado a nivel de física médica para los diferentes fantomas y queríamos ver entonces cómo es su respuesta a esta radiación. Entonces lo que hicimos fue láminas que fueron impresas en una impresora 3D y con la caracterización de nuestro tubo de rayos X, de ese espectro de radiación, pudimos obtener algunos resultados. Entonces, lo que medimos en sí es el coeficiente de atenuación y lo comparamos con el PMMA. Pero lo que hacíamos es, la impresora 3D hace esa impresión con diferentes porcentajes de relleno. Entonces, miramos cuál fue el porcentaje de relleno que más se parecía en atenuación al PMMA. Entonces, pudimos ver que el PLA es el que mejor se comporta en esa situación y con esto pudimos apoyar un proyecto de investigación, de una tesis de pregrado del Departamento de Física de la Universidad Nacional, en el cual lo que se quería era determinar la dosis fetal en estudios abdominopélvicos en tomografía computarizada. Entonces, la idea era poder adecuar un vientre impreso en 3D con un material que respondiera muy parecido al PMMA y miramos que el PLA con un relleno del 80% podía tener una buena respuesta y lo que hicimos fue simular un vientre de una mujer embarazada, ponerle unos dosímetros TLD dentro y hacer el estudio de la tomografía y obtener algunos resultados de allí. También, además de la caracterización de materiales, también trabajamos en la simulación. Aquí trabajamos, esto ya es algo más técnico del laboratorio, y la idea es de simular el perfil y los porcentajes de dosis en profundidad para determinación de la dosis absorbida en agua de referencia en el laboratorio secundario de calibración dosimétrica. Esta investigación pues, se centra en simular esa dosis absorbida en agua por medio de un software que de hecho es un kit de herramientas basado en Jan4 que se llama Topaz, con el fin de mejorar la precisión y la exactitud de las mediciones en radioterapia externa. También trabajamos en aplicaciones de las radiaciones ionizantes, no solamente a nivel de física médica, sino también este mismo software nos sirvió, por ejemplo, para simular el mapa de dosis de la planta de irradiación gamma. En el Servicio Geológico Colombiano, en la Dirección de Asuntos Nucleares, se tiene una facilidad gamma, es decir, una planta con una fuente gamma de alta actividad, que sirve para esterilización de diferentes productos quirúrgicos y demás. Y queríamos entonces simular todo el recinto en donde se hace la irradiación de esos productos. Entonces, con un estudiante de la Universidad Distrital, se simuló mediante topas, las simulaciones estaban con topas, tanto los lápices de cobalto como toda la infraestructura que está ahí dentro, incluso la piscina que está por aquí abajo, y poder simular entonces cuál sería la dosis. Se obtuvo, por ejemplo, una concordancia del 81.2% con medidas experimentales, es decir, que se tiene una buena concordancia con estos datos experimentales. Aquí está, por ejemplo, esta curva en el cual están los datos experimentales y la optimización de esta simulación. Esta simulación sirve entonces para optimizar esos procesos de irradiación que se hacen en esta planta de irradiación gamma del Servicio Geológico colombiano. Y también de lo que hablábamos entonces de la calibración a nivel de braquiterapia, en ese curso que realizó el organismo en las instalaciones del laboratorio secundario, surgió una gran duda allí, y es que si bien el protocolo tiene unos factores de corrección por el modelo de la fuente que se utiliza. Se utiliza iridio 192 para este tipo de calibraciones. Sin embargo, los modelos de fuente suelen ser distintos y las cámaras de pozo también. El protocolo tiene algunos factores de corrección que se llaman factor de geometría de la fuente, los tiene, pero para un solo modelo de cámara, para las Standard Imaging. La pregunta es, ¿qué pasa si se tiene como referencia otro tipo de modelo de cámara? ¿De dónde podemos obtener estos factores de corrección? Si bien el protocolo no es muy extenso en decir qué hacer allí, entonces lo que se puede proponer es una simulación Monte Carlo con diferentes ensambles de cámara y fuente. Es lo que estamos entonces nosotros trabajando también con la simulación Monte Carlo, de intentar obtener estos factores geométricos para ajustar el coeficiente de calibración de estas cámaras cuando no se tenga una cámara de referencia estándar Imaging. Entonces es otro de los proyectos de investigación que trabajamos con la simulación Monte Carlo. Y entonces aquí está el objetivo, es que podamos determinar el factor de corrección debido a las diferencias geométricas entre distintos modelos de fuente de iridio 192 para estas cámaras de pozo diferentes a las estándar Imaging. Y bien, eso es lo que les queríamos mostrar. Muchísimas gracias a todos.
Muchas gracias a nuestros ponentes. Los invitamos si alguien tiene preguntas. Thank you very much for our speakers. If you have questions.
Muchas gracias. Excelente presentación. Pues todo lo que hacen ustedes es increíble. Yo quería preguntarles, mire, más del 60% de los aceleradores lineales en Colombia están en manos de privados y también de las fuentes de braquiterapia. Sabemos que se hacen algunos cursos por parte del organismo donde se hace un poco complejo acceder por parte de los privados, generalmente, y pues también eso tiene una razón de ser. Son las instituciones públicas las que acceden a este tipo de capacitaciones. Sin embargo, como están en manos de privados, quería preguntarles cuáles son las estrategias que tienen ustedes para la apropiación social del conocimiento y para que esto llegue realmente al grueso de personas o de profesionales que utilizan las fuentes radioactivas en el área médica y los aceleradores lineales. Por ejemplo, este curso tan importante que hicieron de braquiterapia hubiese sido importante si se asistiera por lo menos un representante de cada institución o digamos que se le diera participación a las empresas privadas porque son quienes más hacen uso, o bueno, quienes más tienen acceso en este momento a los aceleradores y demás. Entonces, más allá de una queja o algo así, es cuáles son las estrategias que ustedes tienen, porque es que están mostrando unas proyecciones que son importantes para todos y cómo vamos a lograr que realmente este conocimiento tan importante, tan valioso que ustedes tienen y todo lo que se ha invertido llegue a quienes más utilizan este tipo de tecnologías. O sea, o cómo nosotros como privados podemos acceder a, al conocimiento que ustedes tienen. Cómo se va a llevar a cabo una relación o un diálogo abierto con las empresas privadas para poder tener, digamos que todos estos avances en manos de quienes más los utilizan. O sea, ¿cómo sería? ¿Cómo es ese diálogo que se pretende mantener? Muchas gracias.
Bueno, muchas gracias también por la pregunta. Empezando de pronto por el tema del, poniendo como ejemplo de pronto el curso que se hizo el año pasado, efectivamente esa, perdón, esa restricción de que los asistentes fueran únicamente de entidades públicas obedece al hecho del manejo de los recursos. Es decir, digamos, hay unos recursos, no, o sea, no son tan altos comparados con lo que cuesta realmente. O sea, normalmente para participar en un proyecto, el país hace un pago del 5% más o menos de lo que es realmente el costo de participación real del proyecto. Es decir, si se va a través del proyecto a adquirir, no sé, por poner un ejemplo, 1.000 millones de pesos, el país, pues a través del instituto, debe pagar alrededor del 5%. El hecho de tener recursos públicos ahí ya es un primer impedimento para que organizaciones privadas puedan acceder formalmente a los cursos. Entonces, sí hay una iniciativa por parte de nosotros también de poder diseminar, de hecho es parte de la función del laboratorio, no solamente proveer la trazabilidad. Esto inicialmente lo estamos atacando con el proyecto que formulamos para 2026-2027, con la parte de la elaboración de las guías y la parte de la socialización. Entonces, estaríamos iniciando, digamos, con esta parte de lo que es confirmación metrológica, que consideramos que es uno de los eslabones más importantes y en el que más hay, digámoslo así, debilidad en el país. El único inconveniente acá es que no va a ser algo certificable. Es decir, los documentos obviamente son unas guías, son libres, y las actividades que se realicen de socialización, hay una terminología que, bueno, en algunos casos se comparte, en otras no, que es la de social del conocimiento, ¿no? Apropiación social, gracias. Apropiación social del conocimiento. No pueden ser certificables, pero la idea es que las hagamos de acceso público. Ahora, sobre los cursos, por ejemplo, el regional, que vale la pena también, digamos, resaltar que es un curso que se hizo acá y que el organismo realmente lo hizo en varias regiones del mundo. De hecho, en este momento está haciendo uno, va a ser uno en Italia. El contenido es básicamente el mismo y muchos de los ponentes internacionales también son los mismos. Entonces, pues para nosotros fue un gran honor, obviamente, haber tenido la oportunidad de ser anfitriones. Si hubiéramos querido que pudiera ser de acceso un poco más amplio, pero pues fueron las restricciones del organismo. ¿Qué podemos hacer y qué estamos planteando nosotros hacer? Replicar ese curso, o sea, replicarlo con aliados, por ejemplo, con los que tenemos. Nosotros tenemos convenios no solamente con entidades públicas, sino también con algunas privadas. Replicarlos, digamos, tomar esas instalaciones, poderlas usar como sede para replicar estos cursos y darle de pronto un alcance un poco más sí, a nivel nacional. Es decir, acá teníamos 22, 23 asistentes regionales. En principio podríamos replicarlo por cuestiones de espacio y eso más o menos mantener la misma proporción de asistentes a nivel nacional y esto ya permitiría pues de pronto empezar a tener ese alcance. Tendríamos de pronto la misma restricción de que los cursos, o sea, no podrían ser un curso, o sea, una capacitación formal, sino más bien algo de divulgación, pero esencialmente el contenido podríamos mantenerlo y podríamos replicarlo. Eso es más o menos lo que estamos planteando para este año, posiblemente para proyectos posteriores vamos a tratar de poder darle el alcance. No podemos obviamente comprometernos a que así va a ser porque depende de restricciones también pues, del país y del Organismo Internacional de Energía Atómica. Muchas gracias.
Qué pena, tengo otra pregunta. En algunos centros se han hecho algunas investigaciones que van pues concordantes con lo que ustedes han mostrado. Y como la idea es sumar, les quiero preguntar cuál sería la ruta para hacer un trabajo conjunto con ustedes como institución pública, pero de parte de un privado, pues para aunar esfuerzos en pro de lo que hacemos a diario.
Sí, yo creo que es bien importante esa parte de trabajo conjunto. Nosotros lo que hacemos es, generalmente vienen estudiantes, les proponemos temas o vienen con temas y los apoyamos, pero también se puede con una carta de intención, sí, nos sentamos, miramos cuál es el proyecto, en qué podemos colaborar nosotros, en qué pueden colaborar ustedes, y presentamos ante un comité de la Dirección de Asuntos Nucleares y es el que nos va a dar el aval para seguir con el proyecto. Entonces es tener la intención, yo le puedo dar mi correo para que empecemos a tratar esos temas. Pero sí, son bienvenidos todas las intenciones de proyectos de investigación conjuntos.
Ok, ¿o alguna otra pregunta? ¿Qué tal? Buenos días. Excelente trabajo, o sea, todo lo que hacen me parece, siempre me ha parecido muy interesante. Pero tengo una pregunta con respecto a la verificación, o sea, si bien el servicio geológico, o digamos que tiene en sus manos la verificación o la trazabilidad de las dosimetrías en radioterapia, y pues ahorita qué chévere que vayan a abrir para radiodiagnóstico porque hace un montón de falta. ¿Ustedes también tienen algún servicio, tienen proyectado poder revisar la trazabilidad de las lecturas dosimétricas personales? ¿Eso por qué lo digo? Porque si bien el Ministerio de Minas en su entonces pues daba o dio las licencias para algunos laboratorios a generar o prestar el servicio de dosimetría, ¿quién verifica que esas lecturas dosimétricas realmente se estén haciendo como debe ser? eh, Pregunto yo, o sea, tengo una empresa de dosimetría, pero a mí, ¿quién me garantiza que realmente el proceso que ellos están haciendo está bien hecho y que efectivamente esos reportes dosimétricos que me entregan, pues realmente son pues verídicos? Entonces, no sé si eso está en manos de ustedes o si lo tienen pensado para de pronto más adelante poder verificar esos procesos con las empresas que ofrecen el servicio de dosimetría personal.
Muchas gracias. Esa pregunta tiene un impacto grandísimo en la parte de protección radiológica, principalmente de los trabajadores con radiaciones ionizantes, y nos unimos a la preocupación, porque también lo somos. ¿Qué sucede? Que la regulación que hay sobre los laboratorios de dosimetría, ya tiene bastantes años esta regulación, y en otros países, por ejemplo, se exige que los laboratorios estén acreditados, que haya una evaluación independiente de un órgano acreditador. No es el caso de Colombia. Aquí el servicio de dosimetría debe adquirir una autorización por parte del Ministerio de Minas y Energía. Tiene unas condiciones, esa evaluación. ¿El procedimiento actualmente cuál es? Perdón. El laboratorio de dosimetría le envía los dosímetros al ministerio. El ministerio nos solicita la irradiación a nosotros. Nos dicen las dosis que requieren. Nosotros hacemos la irradiación. Esta irradiación pues es trazable a través de nuestros patrones. Es básicamente la misma trazabilidad que se tiene para la calibración de los dosímetros de lectura directa. Entonces, posterior a esto, el ministerio envía de vuelta los dosímetros a el laboratorio de dosimetría, y allí se leen y se comparan las dosis reportadas por el laboratorio con, con las dosis que nosotros, pues con el reporte nuestro. Eso, digamos, es una primera instancia de comparación, aunque no es una intercomparación formal. Nosotros también consideramos que esto se puede llevar un paso más allá de pronto a una formalidad, no solamente, digamos, al inicio de la autorización, sino periódicamente. Tengo entendido que periódicamente también hacen esto. Digamos que cuando nos envían a nosotros los dosímetros, los hacen de una forma anónima. O sea, el ministerio los hace llegar de una forma anónima. Nosotros reportamos las dosis a través de pues, un canal seguro y eso es totalmente confidencial y son ellos quienes se encargan de hacer la evaluación. Esta inquietud, pero a ese nivel. ¿Por qué a nivel de inquietud? Porque nosotros como laboratorio, si bien el servicio biológico tiene delegada la parte de la regulación, de la parte de inspección a las empresas, esto corresponde a un área diferente a la cual nosotros como laboratorio pertenecemos. Es decir, nosotros no estamos vinculados a la parte regulatoria y tenemos que siempre tener nosotros mucho cuidado en que cada actuación que hacemos respete esa separación que hay. Obviamente esa inquietud, no solamente como laboratorio, sino como usuarios de material radioactivo, a la autoridad reguladora en función de que es algo que de pronto se puede formalizar un poco, un programa de intercomparación, así como lo que queremos hacer para la parte de radioterapia, un programa así similar se puede hacer. La infraestructura técnica ya está, pues está el sistema de irradiación es trazable. Entonces, ¿qué seguiría ahí? Que nosotros no tenemos digamos, ni la autoridad ni una acreditación para realizar programas de intercomparación. Esto se hace a través de otra norma que es la ISO 17043, si no me traiciono la memoria. Nosotros no estamos acreditados ni tenemos la intención de hacerlo pues para esta norma, pero quien sí tiene la autoridad realmente es el Instituto Nacional de Metrología. Entonces, nosotros sí le hemos transferido esa inquietud a la autoridad reguladora y le hemos hecho saber que la infraestructura está, la infraestructura técnica están los convenios con el Instituto Nacional de Metrología y es algo que se puede llevar, ¿sí? Más allá de eso, realmente nosotros como laboratorio estamos un poco limitados por esa razón que le digo, porque estamos separados del área regulatoria. Entonces, esta inquietud, que es bastante válida y apoya muchísimo las iniciativas pues, del laboratorio, podría hacerles de pronto una invitación, pues muy respetuosamente, a enviar esas inquietudes a la autoridad reguladora, que es el Ministerio de Minas y Energía, y esto, o sea, realmente esto apoyaría, esto ayudaría muchísimo a que esta iniciativa se lleve a cabo. De hecho, al hacer esto, básicamente lo que se estaría haciendo uno como ciudadano puede también exigirle a las autoridades reguladoras. Entonces, esto se puede hacer a través de eso. Ellos también pues no han sido indiferentes realmente, ellos también han hablado un poco con nosotros acerca precisamente de la viabilidad de poder hacer esas intercomparaciones. Es algo que posiblemente en un panorama de pronto de un medio tiempo se pueda realizar. Entonces de pronto sí es como, vamos, hablando entre usuarios, que también lo somos, de radiaciones ionizantes, es algo que los instaríamos a hacer. O sea, es algo que apoyaría bastante el país. Y sí le cuento que no son los primeros que nos han hecho esa inquietud. Hay bastantes usuarios que nos lo han hecho y muchos de ellos ya se han dirigido también a la autoridad reguladora. Nos los han hecho saber la autoridad reguladora y pues lo que le digo, o sea, les hemos hecho saber que el brazo técnico necesario pues está disponible para eso. Gracias.
Ok, preguntas.
Bueno, yo quisiera hacerles dos comentarios y una pregunta. Entonces, uno de los comentarios primero es decir que como Universidad Nacional, pues también queremos agradecerles porque hemos pues, recibido apertura de parte de ustedes para la realización de trabajos, visitas y demás. Y esto pues es efectivamente muy importante para la formación de los estudiantes. Siempre han estado con los brazos abiertos. El segundo comentario de pronto respecto a la pregunta que hizo el doctor Merchan. La Nacional también ha sido o es contraparte de proyectos regionales. Justamente el profesor Luis Agullas es delegado de otra serie de proyectos regionales y la restricción para participar en los cursos realmente no es una restricción directa a participar, sino a ser financiado, por ejemplo, para viajar y para ser certificado. Y en nuestra experiencia, mía propia, justamente, tú puedes ir a los cursos. Si tú te puedes financiar y tú puedes asistir, tú puedes ir a los cursos. Que no vas a tener la certificación oficial del organismo de energía atómica. Esa es la restricción, hasta donde entiendo. Porque, pues, también como organizadores de cursos o como participante en otros, pues ya nos ha pasado. Ese es como el segundo comentario. Y la pregunta iba, pues justamente porque tenemos estudiantes aquí, ¿cuáles creen que son esos proyectos que ustedes están desarrollando en los cuales específicamente los estudiantes de física médica podrían participar y unirse y contribuir?
Principalmente en lo que estamos hablando de braquiterapia, ahí hay un buen tema que puede ser muy afín a los estudiantes de física médica. Estamos intentando, pues, adaptarnos al nuevo código, a la nueva revisión del código de dosimetría de braquiterapia y allá hay pues, unos buenos interrogantes que se pueden trabajar como un proyecto de investigación. Entre esos el factor de corrección por diferencia de las fuentes. Eso puede ser. Bueno, sí, en radiodiagnóstico pues también estamos trabajando en esa implementación, pues allí también hay cabida. También trabajamos alguna vez supervivencia celular, ¿sí? Hicimos con Juan Manuel, utilizamos el radiador que tenemos de radioterapia para poder hacer un estudio muy interesante de supervivencia celular. Entonces, hay muchísimos proyectos que se pueden trabajar con el laboratorio secundario. Es solo, pues, la intención, si tienen una idea, pues, podemos sentarnos y mirarla. Y si necesitan también algún proyecto, pues tenemos algunos.
Muchas gracias. No sé si en el chat hay preguntas. Maybe online, any question? Nuevamente, muchas gracias a Julián Niño y Camilo Calderón, los invitados del Servicio Geológico. Entonces, vamos a ir a nuestra hora de almuerzo. Los invitamos a la próxima charla de cierre a cargo de la profesora Sofía Enrich y a la clausura del workshop. A las 3:30. We are going to have
Sofía Enrich from Paris Saclay. Professor Sophie is going to talk about different projects in medical physics at Paris Saclay. Please, Doctor.
Thank you. I'm way. Is it okay? The mic? Okay, great. So thanks for being still here. I hope you have still a bit of brain energy for this last talk, because actually this afternoon I will talk to you about the project we are conducting in our team, which is a team which is a interdisciplinary team, but there is many biologists. So the project I will present you is an interdisciplinary work between medical physics and radiobiology, actually, targeted, of course, about flash radiation. So I hope you're not too fed up with flash. For the people that have been that have not been here in the first day, fortunately, Angela this morning has done a great review of what is the flash effect, so I won't do it again. I just wanted to remind you something I have shortly presented before, which is one of the biggest projects of the Institute Curie for next year, which is the implementation of a brand new machine, which would be a very high energy electron therapy system. So this is a technology that is currently not in clinic at all. So this is really a research progress project. The machine is not built yet either. With our team, our work for now is to prepare some biological experiment in order to decipher more what condition of irradiation is able to elicit the flash effect, and also to prepare some testing for the machine when it will be built. So even if it's not completely clear of how this machine will function, for sure we want the project is to build a linear accelerator that is able to accelerate electron up to 50 to 200 MeV. We'll see how much exactly, but that's for the moment that's not the priority. It was chosen because we hope that it will be a technology which is cost effective compared to proton therapy, that may be able to deliver treatment plan of equal quality. And of course, this kind of machine will enable ultra high dose weight. So hopefully we'll able to create the flash sparing effect of LC tissue. The first planned target to a future, really in the far future, clinical trial have been chosen to be brain, because the flash effect has been already vastly demonstrated in brain, in lung for the same reason, and this is also a bit of our specialty. And in pancreas, for the moment in pancreas, the flash effect has not been demonstrated by any teams in the world, but still it's a goal, because you may know that this is the pancreatic tumor are localization which are very difficult to treat. In general, pancreas cancer is diagnostic as a very advanced stage, and for the moment the radiation therapy doesn't really work. And also another target is way irradiation. I will introduce that in the later part in the talk. But in our team, we are focusing in lungs because it's our specialty, and lung radiation. So this is on that localization. I will present you some experiment. As the future VHE machine will be a linear accelerator, that means that we have to deal with the temporal structure of a linear accelerator. So I have already presented this slide before, but just to remind you that flash linear accelerator will deliver the radiation by pulse, exactly as a medical LINAC, but the dose per pulse will be extremely high, at least a few gray per pulse. It is even possible to deliver a complete treatment session with only one pulse. Technologically, it's possible with a linear accelerator. And that means that in general, when, for example, if we deliver a treatment on mice of 9 gray, we will deliver only a few pulses, like maybe 1, 2, 3, maybe 4. So a very limited number of pulses. And of course, as we are studying flash, we will deliver this treatment at a very high average dose weight. So the average dose weight will be simply the total dose divided by the total time of irradiation. Which can, with this kind of machine, can be much higher than 100 gray per second. It can even reach quite easily 1,000 gray per second. However, as the time structure of the irradiation is pulsed, that means that there is other parameters than the average dose weight that may be important for the flash effect. So basically, one of the questions that we are addressing with the team is average dose weight the only critical parameter driving the flash effect in lung tissue? I will always precise, if I forgot, you have to keep that in mind, that it's always limited to what we are looking at, which is lung, And even sometimes it can be divided into acute affecting lung or late affecting lung. In biology, no one generalize without a lot of caution. So maybe it's completely possible that some other group working on some other organ can find different results because biology systems are so complex. There is so many interaction with action, retroaction, and things like that, that it's pretty possible that you can have a different effect. So I will be cautious, and everything that I will tell you is valid for lung tissue. So the first question is basically, is the dose purpose, which is well, a specifically high in ultra high dose weight irradiation, is the dose purpose matters. And in particular, can we preserve the flash sparing effect on healthy tissue, even if the dose purpose is a bit low with bracket, because it still will be quite much higher than in a conventional irradiation, but low in the flash range, let's say, even if we keep an average dose weight at the level that is known to elicit the flash effect. So that's the first question. And the second question, which is a question that is, for me, I think it's very important, is that we always speak about the average dose weight as maybe we want to set a threshold to say, okay, we need that limit, that lower limit of dose weight to elicit the flash biological effect. But in general, all the experiments that are done in preclinical studies are done at only one doses. So that means that you can say what is the dose weight, and you can say what is the irradiation duration. And of course, both parameters are linked, because this is you have only one doses. But what if you want in the end to treat patients with a dose which is completely different? In that case, when will you use as a threshold the dose weight, or will you use the irradiation duration? Because if the dose is different, for example, if you want to deliver a dose which is twice as large, if you want to keep the irradiation time the same than the one for which you have demonstrated the flash effect, that means that you have to double the dose weight. And conversely, if this is the dose weight that is important, that means that your irradiation will last twice longer if you deliver a dose which is twice high. So this is a question you will see is not necessarily easy to answer with experimental condition. So first, it was already quite very well presented by Valentina and Sebastian, so I don't have to do it again. But this is a machine that is installed in Institut Curie in the research center that belong to our teams, and on which we are doing all the experimentation. So this is low energy LINAC. It can deliver a beam at 5 and 7 MeV. So we always use 7 MeV for experiment now. And it has the specificity to be, so as it is an only electron mode LINAC, to be operated with what we call applicators. So unfortunately, you cannot see them so much in this picture because they are in PMMA. So but there is this plastic tube that have different diameter but different lengths. And actually, we use this applicator to modulate the dose purpose. Basically, it's very simple. This is just because they have different lengths, so you are more or less close to the source, and that means that you all know the law of the inverse square of the distance for the dose. So that means that the closer you are, and the higher dose that you get. So that means you have also higher dose purpose. The other way we have with this machine that was particularly designed to be able to tune all the parameters. So the other way to tune the dose per pulse is to change the pulse duration that we call in general the pulse width or the pulse length. So that means that the pulse duration can vary between 0.5 to 4 microseconds. And remember that each pulse contains a very high dose. So that means that if you change a little bit the duration, you can change the dose per pulse from 1 gray to 2 gray and 3 gray, for example, or even lower if we are closer to the source. And also, if we change the energy, we also change the dose per pulse, but in general, we don't want to change the energy within the experiment. And if we want to adjust the average dose weight without changing the dose per pulse, we will simply play on the pulse repetition frequency, which is the inverse of the time interval between two pulses. And this can be tuned for 1 Hertz to 250 Hertz, or even higher if we use short pulse length. So that means that we can tune independently the average dose weight and the dose per pulse with all that parameter. And you can see, you can see on that table that we can reach quite a high range of different dose per pulse and average dose weight. And we have played with that to look how the sparing effect of the lung can be monitored with respect to all that temporal parameter. In the paper that is always to introduce the flash effect, the paper of Vincent Favredon published in 2014, the endpoint, so this is what we are looking at in biology, the endpoint was the radio-induced lung fibrosis. So that means that we irradiate the mice. So here you see a picture with the setup. So the applicator, you don't see it very well, but it's just here. And here we have a collimator that is able to limit the radiation fields to the mouse thorax. The mouse is there, it is anesthetized during the treatment, and it is treated in upright position. So we irradiate the whole thorax like that, and then we do a follow-up of lung fibrosis. So in the paper of Vincent Favredon, the follow-up was done, well, the quantification of the fibrosis was done by looking at histological slices, which is, well, it was a long time ago. It's not something that we can really do currently, because basically you need to sacrifice some mice at different time points, because the histological slices, as you can imagine, it's a piece of lung. So what we do now is to do a longitudinal, in vivo follow-up with a CT scan. We also have in the lab just next to the accelerator bunker. You can see it here, a small micro CT imaging system. And with that, as we are looking at the fibrosis in the lung, the CT is a good imaging modality because there is a contrast between the fibrosis, which is a densification of the lung tissue, and the normal tissue, which is an aerated tissue. So the density is much less, and so it creates contrast on a CT scan. So, for example, here at with the conventional irradiation, you can see that the lungs is full of dense tissue. However, it is still quite difficult to quantify fibrosis, especially where there is a lot of fibrosis, because you cannot decipher between the earth and the arteria and the fibrosis. And you have to remember that we want to fine-tune the temporal parameter of the irradiation. So basically, we want to do a lot of ultra-high dose weight irradiation and change a little bit a parameter. So we expect not such a change that when we compare conventional dose weight and ultra-high dose weight. And that means that if we want to do that with lung fibrosis, it will be very difficult to decipher between a bit of fibrosis or a lot of fibrosis of something in the middle. Plus, we have to take into account the biological variability of the animals. And we know that even if we deliver exactly the same irradiation, the apparition of the lung fibrosis will be quite heterogeneous. And the last reason is that it takes at least 5 months to see the fibrosis appear. So it's a bit long to wait for a result. So what can we do for that? basically what we want to do is to use a method that is able to that is more quantitative, on which we can count things, and actually we will rely on the hypothesis that the flash radiation therapy spares specifically the cells which are in proliferation. This is an hypothesis based on well, the result of our lab, but also the result of a lot of different research team. And this is something that has been seen in different organs, like the brain, like the intestinal crypts and all that. So it can be considered like maybe a general result that you will, when you will irradiate, you will always decrease the number of cells that are still able to proliferate, but you will spare it a bit or quite a bit when you will irradiate in flash compared to conventional. So basically, we wanted to do a method where we are able to count the proliferating cell. So here I put this nice picture, quite big because I find it really, really nice. This is a microscope image of a small part of a lung. So here you can see the alveolar of the lung. What you can see in blue, it's the nucleus of all the cells. So basically the blue staining is called DAPI. It's a very basic staining that will stain the nucleus of every cells, so we can see them under the microscope. And on this image, you can see a few of them that are red, and these are the proliferating cells. And I will just explain why we do that. There are the proliferating cells. So this is the method we have developed in the lab, mainly developed by Maxime here, who was a PhD student. Now he has finished his PhD. He's now in Japan. And Charles Fouillade, which is our team leader. And they are very good biologists. And as you can see on that picture, maybe we won't let them irradiate anything because they will just put something in the middle of nothing. That was just a fun picture. So what is the method? So it's a method that will allow us to look at the effect of the irradiation at the very early time point, which is 24 hours after irradiation. So what we will do is we take the lung of a mouse, we fill it with agarose to make it swallow, and that allow us to cut the lung in very thin slices. And we will call that organotypic lung slices. We use for that a specific device, which is called a vibratome. And with that, we end it with thin slices of lungs of 300 micrometer of thickness and about 7 to 8 millimeter diameter. And what is important is that this slice is still alive. It recapitulates all the lung architecture. So you have all the different cells, and they are placed at, well, they are close to each other as they are in the lung, and they continue to interact, and they continue to proliferate in the specific medium to nourish them for, let's say, 24 to 48 hours. And after that, they begin to do strange things that are more linked to the fact that they are not in a lung anymore. But this very nice model allows us still to investigate what is happening after irradiation. So after the slices are made, then we irradiate them, and we irradiate them with conventional flash and different subversion of ultra-high dose rate. And after the irradiation, they are incubated for 24 hours in medium that contain something called EDU. And EDU, it's an analog of component of the DNA, which is fluorescent in red. So basically, when a cell will divide to multiply, if you have some souvenir of your biology course, you remember when where there is a mitosis of a cell, the DNA will multiply so that you can have the double amount of DNA and you can make 2 cells instead of 1. So that means that the cells will need to create some DNA, and the cell will catch the component of the DNA in the medium if it's available. And basically, it will catch this EDU thing, which is an analog of the thymine, which is one of the 4 components of the DNA. This is the T of CGT letter of the DNA. And it will use, the cell will use that fluorescent protein to incorporate into its DNA. And then all the cells that have been proliferating during this 24 hours and incorporate this fluorescent protein will be in red in the microscope image after. That is the same that I showed you before in larger. So we are able to count the number of cells that have been proliferating during the past 24 hours on the microscope. And if we do that, we are able to demonstrate that we have more cell proliferating after flash irradiation than after conventional irradiation. So when we developed that model, we first had to validate this model on a different points. The first point is, can we really have a differential response with those? Because we want to show a sparing effect toward irradiation. So if the thing that we are looking at is always the same, whatever the dose we deliver, we won't see any difference for sure. So the first thing we did is dose escalation. And you can see here the dose response of the number of proliferating cells. Well, basically, in that case, this is a proportion of proliferating cell compared to a slice that was not irradiated, because you always have to keep in mind that a biological sample can be quite different day to day, so you always need a control. So in that case, this is a non-irradiated slices. And you can see that you have a nice exponential decay that is as a response to the dose. So we are happy with that. The second thing is that we want to, first, we want to be sure that we can see a differential response when we irradiate in flash and conventional. Otherwise, of course, we can change our model. And here you can, so here we deliver doses of 3 gray, 6 gray, and 9 gray. And we see that we are able to see a difference when we deliver 6 gray or 9 gray. So I will just stop a little bit to explain you what is the difference in biology, because it's quite different than in physics. So in biology, where basically all experiment can be described as you have 2 conditions, 2 results, and you want to know, as we are looking at still something biological, which will have a quite heterogeneous response, as you can see with the number of points that are on that graph. It's quite spread out, and it's not like if you measure something in physics. So as you will have, for example, these 2 different response. In blue, it's flash, in red, it's conv, and you want to know if it seems that the average value of this point, which is the number of proliferating cells per field of view, the average value is different. But as we have quite heterogeneous, it's quite dispersed response, we want to know if that the difference on the average is just due to it's just because of random, or if it's really significant, which is the most important word in the statistical test in biology. So basically, there is a number of statistical tests. The most common is the student test that you may have already heard of. This is not the one that we use here, but I won't enter into that. And the statistical test will tell you exactly that. It will tell you, okay, you have 2 distributions, 2 Gaussian distribution, and can we say that these 2 distributions are really different because there is, with the 2 conditions that you have used, there is a real difference in the biological effect, or is that difference is just due to the hazard, exactly as if I divided this amphitheater and I measure the eye of everyone, but probably the average eye on the left side will be different than of the right side. But can we drive a biological rule of that? Of course, no. It's just because we have a very limited sample, and then if you just pick a few of them and you do the average, you won't ever get the same average. So your test will tell you there is two possibilities of the result of the test. Either it will tell you, yes, I think the difference between your two samples is it's difficult to say, statistically significant with risk of error, which you have to choose, but in general in biology is 5%. So I think the test will tell you, I think that at 95%, there is a real difference between your two conditions. Or the test will tell you, no, I cannot answer to that question. It won't tell you they are not different. It won't tell you, okay, they come, all of that sample come from the same population, let's say. It will just tell you, considering your results, the way the standard deviation that you have in your results and things like that, and the difference of average, I cannot tell you that if there is a difference or not. And this is really important because sometimes there is a misunderstanding and people use this test to say, oh, okay, there is no difference because the test is not statistically significant, which mathematically is not true. Because you can have a test which is not significant only because your experiment is not well designed and you have a too high dispersion on your result, or not enough sample, or everything is very low. For example, here you can see that when we deliver a dose of 12 gray, we don't have, so we have a very low number of proliferating cells. And in that case, basically, you will compare an average which will be maybe 4 proliferating cells in one case and 5 in the other. And when it's so low, it will never be significant. So yeah, just keep in mind that basically we can either say, yes, we have a difference, either, I don't know. And so when I say there is a difference, so on flash compared to conv, that means that the statistical test has come back as significant with a 5% error risk. So basically, here in that case, at 3 gray, we don't have a significant difference. That doesn't mean that we cannot have a flash effect at 3 gray. That only means that in that experiment, the difference is maybe not large enough considering the number of samples that we have to be mathematically significant. It lets you time to process. Okay. So next thing is that we want to check if our model is reproducible, because sometimes in biology they are not reproducible at all. Sometimes we are already happy if we always see a difference, even if that difference is very different, that the amplitude of the difference is completely different in a different case. When the biologists tell you, if you ever work with biologists, when the biologists tell you, yes, it's reproducible, I always see that. That means, for example, that one value is always lower than the other one. And that's all. That doesn't mean more than that. And so in that case, here you have an example of the same experiment with 3 mice. And for us, we consider that as very reproducible because it still looks quite like the same. And the last test that we did to validate the model, this is very important, is to demonstrate that what we are doing is this lung slices, which is called an ex vivo model. So it's not in vitro, it's not in vivo, it's ex vivo, I mean from something alive, but out of this thing alive. So we have to demonstrate that this ex vivo model is representative of what would happen in vivo, which means in the lung of a living animal. So for that, what we did is that we irradiate the mouse alive, of course, and we inject some EDU still alive. And then we sacrifice the mice and we do the slices and we count the proliferating cell. And you can see on that result, we did that a lot of times. That's why there is so many points. We have really similar distribution after conventional irradiation and flash irradiation than in our ex vivo model. So of course, we won't continue to do that because it's very long, it's very cumbersome, and it needs a lot of animals. And for ethical reason, again, we try to reduce the number of animals. Okay. Yes. So we have our in vivo validation. So we are happy with our model. We consider it as a good model to evaluate the effect of radiation treatment. So in that case, we use it for flash, but we also have tested if we can use it for combination between radiation and chemotherapy. And you can use it basically to evaluate a lot of different irradiation techniques. The only limitation is that it gives you hints of what is happening only on the 24 hours after irradiation. This is really important to keep in mind. This is a critique that we have, is that doesn't tell us exactly what will happen at the late effect. Okay, so now what we have done first, we have done a dose weight escalation to see if we can see a threshold in average dose weight. It's a kind of reproduction of what has been done that Angela showed this morning on the brain on the brain of the mouse by a team in Switzerland. And for that, the only parameter that we change is the pulse repetition frequency. So basically, if we increase the pulse repetition frequency, we increase the dose weight, the average dose weight, but the dose per pulse stays the same. And we got this result. And basically, we compare each result with the conventional irradiation, and we look at which conditions are statistically different from the conventional. And what we see is that compared to conventional, the sparing in proliferation is very significant when the dose weight is equal or above 340 gray per second. It's still significant, but it's notably reduced when the dose weight is equal to 220 gray per second. The numbers are a bit strange because we did a round number of frequency, which wasn't so smart. And that we lost completely the difference with the conventional when the dose weight is equal or below 110 gray per second. So again, a criticism was or will be every time that, okay, but how that for 1 day after irradiation is representative to what will happen for the late effects, which are the effects that we try to avoid on the patient. So to check that, we did again the follow-up of the survival due to the pulmonary fibrosis for mice that we have irradiated at conventional dose weight for 40 gray per second, which is the value that was on the first paper, and 400 gray per second, which is above the limit of 340 gray per second. And suspense. So then we look just at the survival. We just monitor the mice with a CT scan to check that if they die, or well, basically we don't let the mice die. It's forbidden. So if people found a dead mouse in the animal facility, they come to us and they yell at us. So basically, when we say the mouse dies, that means that either she lost too much weight, either she feel a little bit unwell because his fur is not nice or things like that, or she behaves strangely and all that. So there is a list of criteria that tell you, okay, the mouse is not good, and then we check she had fibrosis with a CT scan, and then we sacrifice her. No, I still don't have any. Okay, thank you. So basically, the result of that experiment was that both conditions, 40 and 400 gray per second, yield a better outcome in survival than the conventional dose weight, but we have a much higher survival when we use 400 gray per second than 40 gray per second. So it is consistent with what we can saw here. That maybe the flash effect is not completely on-off, but there can be an optimization of the sparing effect. So now that we know which what kind of average dose weight is able to elicit a significant sparing with that model, we will use this average dose weight, but we will tune the dose per pulse to see if there is an effect of the dose per pulse and if there is a minimum dose per pulse that need to be delivered to keep the flash effect, while keeping the average dose weight at 340 gray per second. And basically, very interestingly, what we see is that we need at least 1.5 gray per pulse, because when we are at only 1 gray per pulse, keeping the ultra high average dose weight, we lost the difference with the conventional, which is very interesting because, I mean, it's not particularly difficult with that device to achieve 1.5 gray per pulse, but some of the, for example, a modified clinical LINAC generally yields more around 1 gray per pulse. Again, that is valid in that model. That doesn't mean that for something else you need that, but in that model, it's particularly striking. Then on the other part of the spectrum, we wanted to know if it wouldn't be better to deliver only 1 pulses. Because basically, if you deliver only 1 pulses, you don't have the time interval between the pulse, which, if you remind the picture, is much longer than the pulse duration because it's the order of tenths of millisecond, whereas the pulse is in the order of microsecond. So basically, if you deliver all the doses, like your 9 gray, is 4 microseconds, your dose weight is much higher. It's not like 100 of gray per second, it's like 1 million gray per second. So maybe it's even better with a dose weight of 1 million gray per second. And unfortunately, in that case, we didn't observe any amelioration with only 1 pulse. We get exactly the same results and with 2 pulse or 3 pulses. Well, unfortunately or not, because I mean, from the technological point of view, if we say to the manufacturer, okay, we want a machine that is able to deliver all the doses in 4 microseconds, maybe they won't be so happy. Okay, then we produce this experiment with a dose of 6 gray, which allow also us to see a difference, even if it's a bit less noticeable. And well, basically what we wanted to do is try to see if we change the dose, maybe we can decipher between the importance of the dose weight itself of the on the radiation time. And unfortunately, well, this experiment doesn't really answer the question. Basically, we get exactly the same result, that we need a minimum of 1.5 gray per pulse, which is interesting to know that this result is also valid with lower doses. And that if we have a dose weight of 220 gray per pulse, we still have the difference with the conventional. However, in the previous experiment, we see that we also have a kind of difference at 9 gray, and it's really difficult to say if a difference is higher than another difference. So basically, it didn't quite answer to our question for the radiation time versus the dose weight, but at least it comforts us for on the result, on the importance of the dose per pulse. So yes, this is a summary. Basically, if we want to investigate more if the radiation time matter more than the dose weight, we would need to be able to do an experiment with higher dose, and then we will have a higher difference between the radiation time and the dose weight. Technologically, we can completely increase the dose weight. But unfortunately, this model in particular, as it is, give us too many proliferating cell, too low number of proliferating cell at 12 gray. So it's not significant. So we are currently working on just expanding the method of image analysis on the microscope to be able to count the cell on all the slices and not only a limited number of area, without that take us like days and days. And what is the perspective? If you were there on the first day, one of the first questions I had in the audience is, yes, okay, you show sparing of the LC tissue, but what about the tumor? And of course, this is a very good question. This is always a question. The flash effect is defined by the sparing of the LC tissue while maintaining an anti-tumoral efficiency. So we want to be able to do this kind of test in in a tumor and in an LC tissue, which is the environment of the tumor, because we can also imagine that if you have a lung cancer, the lung tissue surrounding the tumor is not really normal lung tissue. It's probably modified by the presence of the tumor. So for that, we need a model on which we will have a tumor on the lung, which is called an orthotopic model, which means that the tumor is where she will naturally be. So we are working on that. Oops. Sorry. We are working on that. It's not so easy to make a mice develop a lung cancer. So basically, what we are doing is injecting tumor cell in the tail vein, which is not very easy. But if you are able to put the cancer cell in the blood circulation, it will directly go to the lung. It's a bit, if you have maybe the people have tell you that when you did the brachytherapy seminar. If you inject some iodine seed in the prostate, and if one is escaping from the prostate, you will find the seed in the lung, because everything ends up in the lung and is stuck in the lung because the capillary become very thin. And so you can see here that the preliminary results are quite encouraging. We follow that with our CT scan. And you can see on the CT scan a nice lung metastasis that has appeared in some mice. So it's still the model still need to be our skill needs to be improved to get that each time. And then after that, we will be able to cut some slices on which we have a part of the slice will be the tumor, part of the slice will be the tumor microenvironment, and part of the slice hopefully will be the LC tissue. Okay, now another question, which is maybe one of the most important, because a lot of, except the feasibility clinical trials that I have presented on the previous seminar, but actually there has been no trial or experiment that has demonstrated a difference between conventional irradiation and flash irradiation on humans. You can understand why, because we don't want to test like that. But actually, there is none. So what we wanted to do is to test that at least on human tissue. And so for that, we did exactly the same thing, actually, because we were lucky enough, thanks to collaboration with another hospital in Paris, to get some samples that are from a cancer patient lobectomy. This is when they are operated for their lung cancer. Sometimes the surgeon remove the whole lobe of the lung, or at least a big part, and that means that there is a big portion of LC tissue, not only the tumor. So the tumor, it's needed for the anatomopathology examination, but the LC part of the tissue, they accept to give us to us a really small part. And we do exactly the same thing. We do some slices and we irradiate it either with conventional or with flash with the same patient, which is very interesting, of course, because we can expect even higher heterogeneity in humans than in mice that are more or less clone of them. And we count the proliferating cell. So we, within almost 3 years, we were able to get 19 patients. So you see, it's quite difficult to get this patient sample because for a lot of reasons. But basically, first, of course, we need the specific agreement of the patient, and sometimes the medical team they just don't ask, or the patient say no. We need also the surgery to be early enough in the day for the pieces as time to go to the anatomy pathology lab, which close at 6. And if it's after 6, basically they just do the examination the next day, and for us it's too late. There has been a lot of case where we just lose the sample, so it's quite difficult, but we still are quite happy to get all these 19 patients. And what is interesting is, so we take everything that was proposed. There was no particular plan for the patients that we wanted, but luckily we have more or less half male, half female, and they have a lot of different background. Some of them have received some chemotherapy before, some of them have received some immunotherapy before. They have different smoking background and things like that. So it's maybe for the statistics, it's a little bit too heterogeneous, but it's still interesting to have a lot of cases. So here you have an idea of the variability of the number of proliferating cells in the sample prior to irradiation. So you can see that, sorry, yes. You can see that, well, for most of them, the average is more or less the same, except for three patients, patient 12, 13, and 16, for which they have a quite significant higher number of proliferating cells. And interestingly, it's not a demonstration, it's definitely not statistically significant, but interestingly, this is a 3 patients that have received immunotherapy prior to the surgery. Then if we do our test of conventional versus flash irradiation, we were really happy to see that 18 patients over 19 response to the flash radiotherapy. That means that 80 patients show a significant difference on the sparing of proliferating cells in flash radiotherapy versus conventional radiotherapy. So this is really encouraging for the clinical translation of this technique to human. We see that there is only 1 patient for which is not significant. We cannot say why. I mean, we cannot, but still we can notice that this is one of the patients that this is actually the one that has the highest basal level of proliferation and that has received immunotherapy. So again, no conclusion, but just this is the only difference on the background that we can notice. So basically, the answer of the question is yes, we can see a flash effect of human patients. And so for the perspective for that study is, of course, to try to convince the anatomopathologist to give us a very small part of tumor. So again, we can validate that we don't have any difference when we radiate in flash on the tumor, because this is really important. Okay. No, okay. How much time do I have? Oh, perfect. Okay, so now I will change a bit of topic and talk about ray irradiation. So ray irradiation is a really hot topic right now. Maybe you in the hospital you have hear about that because actually there is more and more patients that undergo a second irradiation months or even years after a first radiotherapy treatment. This is for a good reason, because this is because basically the progress in the treatment of cancer has been such as people stay alive much longer, and so they have time in bracket to develop a second cancer, maybe somewhere else. In that case, there is no radiation issue, but maybe more or less in the same area. And when you will do the treatment plan, you will end up by irradiated tissues that have already been irradiated. In the case of lung cancer, or more specifically of non-small cell lung cancer, there is a very important rate of relapse. More than 1/3 of the patient relapse with a second tumor in the lung within 2 years. So that means that there is a lot of patients that can potentially be irradiated again. This is, for the moment, this is not necessarily the case. And for the moment, they are not all receiving a second radiotherapy, at least in France. And also there is, this is the case of relapse, but there is also the case when you have a second primary cancer within the same area. So ask for oncologists to tell you how they can decipher between a relapse and a primary cancer, that I don't know, but this add up another reason to do some radiation therapy and to have to irradiate again some tissue. So the clinical studies show that it's a treatment that can have a therapeutic impact. It's worth to irradiate patients; they survive longer, and if they get a second course of radiation therapy. But unfortunately, also the adverse effects of the radiation therapy are way higher than with the standard lung therapy. And in particular, in these studies that encompass almost 600 patients, they get 100% case of fatal case due to the toxicity of the radiotherapy itself, which is of course not the case for normal, classical primary lung radiation therapy. And it can be pretty bad. And from what I have heard, that you can have the aorta just exploded and patient drawn in their blood or something like that. So yes, in the case of radiation is particularly interesting as an application for flash radiation therapy if we are able to spare the LC tissue in that case. And also maybe you know as a medical physicist that in case of radiation, all the those limits at the organ at risk are not valid anymore in case of radiation. No one knows exactly what to do, and for what I have do my own private investigation, asking to any people I know in different hospitals, and they have all different rules of those limits considering radiation. So really, that's a hot topic. Yes. So again, when we design the experiment, we have in biology, it's really important to ask a precise question. It's not like, okay, I will do an experiment and we'll see what happens. So the two questions that we have asked is that in the case of previously irradiating lung tissue, is flash radiation therapy still able to spare the lung proliferating cells? So which means that can we have a sparing on the acute effect? Which in that case, in case of patients, there can be actually a very strong acute effect. And also, are we able to spare the late effects, which in our model is again the lung fibrosis? So for that, the design of the experiment was to give to the mice first, let's say, radiotherapy. For that, we choose the condition that we choose was to do only conventional therapy because we were thinking, well, okay, if no people at some point flash go to the clinics and we have to treat patient in case of irradiation, probably the first irradiation will not be flash. They will have been treated maybe 10 years ago with conventional therapy. So we consider that the first course of irradiation will be conventional, and we choose to deliver a dose of 10 gray, because as we are used to do experiment on which we get lung fibrosis, we know that with this strain of mice, we get lung fibrosis from 13 gray wall thorax irradiation. So normally, anytime with 10 gray, we never get fibrosis. So we didn't want to get any effect. We considered that, okay, this is the first radiotherapy, everything went well. We have no side effects, but still the tissue have been irradiated at 10 gray single fraction, which is quite high dose. And then we decided to wait 4 months. So we didn't know, to be honest, what would be the best delay. A mouse lives for more or less 2 years. So we consider, okay, for 4 months, it's like a few years for a human. And yeah, it was also just for a practical reason because the project was lasting 1 year. And after 4 months, we did different things. So we first irradiated a lot of mice with 10 gray conventional, and then we divided these mice. And for the first pack of them, we did our classical organotypic lung slices tests. So we do the slices of on the previously irradiated lung, and then we re-irradiate these slices. So they have received 10 gray in vivo conventional dose weight, and then a dose escalation of 3, 6, and 9 gray ex vivo conventional dose weight or flash irradiation or flash dose weight. So again, we needed to choose the doses. So basically, we choose 3 gray because we say, okay, 3 gray is 10 plus 3 is 13. So this is the dose on which we get lung fibrosis with a single irradiation session. And we choose a maximum of 9 gray because we want to stay below dose that by itself will elicit fibrosis, and 6 gray to have a dose in the middle. And of course, we keep also, so in that case, our control is not the non-irradiated slice, is the one that has been previously irradiated, but not irradiated a second time. So what was the result of? So again, it was we analyzed the number of proliferating cells 24 hours after irradiation. So what is the result for the acute effect of re-irradiation between flash and conventional irradiation? But we are actually quite happy because we see that we preserve the flash effect on previously irradiated lung. Yes, just so you can even see that between the only one irradiation at 9 gray and the ray irradiation, we have really similar results. Okay, then we want to investigate the light effect, and for that experiment, we also wanted to take opportunity of the fact that we have the proton therapy center of the Institute Curie quite close. So in the proton therapy center, they have developed a lot of setup and organization to be able to irradiate some mice, which is really great because it's not always possible in big infrastructure. And so we will say, okay, yeah, we have to try it with proton. So basically, with our previously irradiated mice, again, we divided the pool and we re-irradiate the mouse with a dose of 3, 6, 9, and 12 gray with electron, and a dose of 6, 9, and 12 gray in proton. The reason why there is not the 3 gray doses is because we did the proton experiment after the electron experiment, and we have already seen that just at 3 gray they did absolutely nothing. The mouse was very healthy, nothing happened, so we didn't redo these doses. And then we follow up the mice for more than 300 days. Yes. So just a reminder of what is happening with a single 13 gray irradiation, which elicit fibrosis. So actually, we were looking for lung fibrosis, but we were quite surprised, well, or not surprised, but to see other side effects that we never see with a single irradiation, even irradiation that end up with the death of the animals. So we see, of course, we see some lung fibrosis or some partial densification of the lung, but we also see something very strange that we when we see at first on the CT scan, we were like, wow, what is this lung? It's completely white with a tissue density. And in the end, when we open the lungs, we see that the lung was full of liquid. So it's not completely clear what it was. We never see that before, but the radiation oncologist told us that in case of lung ray radiation, they sometimes see some pleural effusion. So this may be something a bit equivalent for the mice. Nevertheless, it is deadly, of course. And we also surprisingly see some quite acute skin toxicity, which was not expected because, well, not particularly expected because skin toxicity, this is something that arrive quite with really high dose. In general, you begin to see skin toxicity with dose of above 20 gray single fraction. So that means that in that case, for the skin, the tissue is very sensitive to the fact that it has been previously irradiated, because we see skin toxicity as a cumulative dose of between 16 and 20, but it is as if the skin hasn't recovered at all during these 4 months. Whereas for the lung fibrosis, actually, it was not the case. We have a bit of lung fibrosis with 10 plus 9 gray, which, so normally you don't have any fibrosis at 9 gray alone. So definitely 10 plus 9, it's more than 9 single fraction. But we didn't see any lung fibrosis at 13 gray cumulative, which is 10 gray plus 3 gray, for example. So we see that the different tissues are more or less sensitive to the time between the two courses of irradiation. However, unfortunately, it's quite difficult to do some statistics with that, because first we lose some mice, or we didn't have so many mice to begin with, and as they died of really different side effects, we cannot mix all the different side effects, so we have only 1 or 2 cases of each one. It was really a preliminary study, because no one has never done radiation studies, because it lasts for more than 1 year. So. And so to finish with, of course, the most important was the survival analysis, which is a bit bothered by the fact that we look at different cause of death and not only lung fibrosis as usual, but still, in the end, this is what is important. And what we can see on that, so there is a lot of different curves, but basically there is the electron experiment, the proton experiment, and the dose escalation of radiation dose. So the first thing that we saw is that with the proton, we were not able to see any difference between flash ray radiation and conv ray radiation. That doesn't necessarily means that we lose the flash effect with proton, because again, that was 2 independent experiments, 2 batch of mouse. There was a lot of technical issues that I will spare off. And basically, the thing is that we don't have any difference, but also the mouse that has been irradiated in conventional dose weight has actually survived quite longer than in electron. So we don't know exactly why. It's possible that the irradiation was not complete on the lung, because we see toxicity elsewhere. We don't know exactly. So this definitely needs to be redone. But the good news is that we see that with the electron irradiation, we were able to keep the sparing effect. So yeah, it was basically we see a significant amount of death only with the condition of 10 plus 12 gray. But with that condition, we can see a sparing of the survival when we irradiated the mouse, re-irradiated the mouse in with flash dose weight. So the conclusion of these studies is yes, we can still see a flash effect on acute effects when we re-irradiate some previously irradiated sample. There is a bit of a caveat on this experiment, is that we didn't see much difference between the single irradiation and the re-irradiation. So it's possible that 4 months of delay between the two irradiation is a little bit too much in the way that the tissue seems to have really repair quite well from the first irradiation. So what we want to do now is that we do this experiment, but with shorter time between the two irradiation. Again, it's really difficult to imagine what would be a significant how we could translate the time between two radiotherapy for human to mouse. And in addition, anyway, even for human, it's completely different from case to case. It can be less than 1 year, or it can be 20 years. So we will just probably do a different time interval and see what will happen. And to the question, does the flash effect spare for the late effect? Well, we have seen a lot of different late effects, and for that we definitely cannot tell if flash is less harmful than conventional radiation, because we don't have any the statistics for that. But at the survival level, with the electron irradiation, we were able to observe a sparing in survival in the case of radiation. Yeah, the perspective on that study is, as I said, to change the time between the two courses, and also to test some fractionated treatment for the first courses of irradiation and for the second one. So with that, I show you the team. Well, it's already 2 years old, so some people has changed. Of course, all this work is mainly their work, to be honest. I thank also the Prototherapy Center for their help. I thank you for your attention, and I'm happy to take questions.
Thank you, Doctor. Questions? Okay. First, I'm going to read the question in the chat. It's a question from Professor Maria Cristina. She says, just out of curiosity, Professor Sophie, how do epoxic cells react to flash therapy in osteosarcoma, for example? Have you done any study on this?
Partially. No, we didn't. So for the moment, we haven't looked so much at the tumor. So definitely, it's really our next step. We have done an experiment when we put the slices under hypoxia, because we have an hypoxia chamber in the lab. And what we see is definitely hypoxia change the response to radiation. So we have a less intense response when the slices are in hypoxia. Again, we have to precise that, I mean, in general, we irradiate the slices like this in the air. So there is more or less 20% of oxygen, which is definitely not the level of oxygen in the organism. In the organism, what is called the physioxia, the level of a physiological level of oxygen, is more like 4 or 5%. And so the hypoxia in the organism is like under 3%. And so we did hypoxia experiment, and we see that we still keep the flash effect on that model. Basically, the hypoxia doesn't change anything except that the response is less strong to the radiation. We think that it was not maybe a very good model for that. It's difficult to be sure what is we just put the sample into a hypoxia chamber, but it's difficult to be sure what is the hypoxia level inside the sample. We didn't see anything specific, so we didn't follow on that part. And it was LC tissue, not osteosarcoma or any other kind of tumor.
Thank you. And my question is just for curiosity, as you show us that you made like a comparison between irradiation with electrons and protons. So my question is, how do you did the dosimetry in the proton beams? Do you use the same methodology but for electrons or something different?
Yeah, but first we didn't take part of the dosimetry with the proton beam, unfortunately, because it is really managed by the physicists in the hospital. I know that they do it quite differently because they don't. I mean, again, proton beam is a cyclotron beam. This is a quasi-continuous beam. So that means that you don't have such a high dose per pulse, even if in the flash modality, the dose per pulse is still very much higher than with conventional proton pulse. But still, even in flash, the dose per pulse is lower than the dose per pulse, even in conventional radiation therapy. So they didn't have any issue with the ion chamber. Lucky them. And also they have all the tools of clinical beam. So that means that they have a monitoring chamber, they have some positioning X-ray that I don't know exactly. I think they just did one positioning with X-ray at the beginning of the experiment, and that's why it's the thing is we didn't do this experiment, so it's complicated, but that's why we think it's not completely impossible that there is an issue with the radiation field, because of course not because their field is changing, but because we know that with mice it's possible that they can move a bit in their setup, and it could be enough. So basically they didn't use film, they didn't use the diamond, they used the clinical dosimetry system. So yes, it's a bit different. But other than that, probably, I mean, that doesn't mean that the dose is not the same, but yeah, they don't have to use so many innovative dosimetry systems. They still needed to adjust all the electronics of the beam control for that to be fast enough, I think.
Thank you very much.
Thank you, Professor Sophie. It was a great conference. I have a little bit questions. First of all, the proliferation of the cells. You said that with flash therapy, it's a little bit high. And I have that question. Why is that better? Because I don't know if it's inside the tissue or maybe up the side, but because we don't want to proliferate the cancer cell, right? So I have that first question.
Yes, well, basically, so in normal tissue, the cell are always proliferating. This is just replacement of the cell. So the level of proliferation is really different among the different tissue. In the lung, there is not a lot of renewal, which is necessary. But for example, in the intestine, if you look at the level of proliferating cell versus the ones that are not proliferating, the percentage is much higher. This is probably one of the reasons why the intestine is so radiation sensitive, because this is, I mean, if you are whole body irradiated during an accident, the brain also, if the dose is high enough, this is the brain that will fall off the first, but otherwise you will die because your intestine will be destroyed. This is one of the most sensitive organ. In part, partially because the renewal is so high, and the cells that are in division are more sensitive. But that's a parenthesis. So yes, it's good that the cells are still able to proliferate, because otherwise your organ is not capable of renewing all the cells that naturally die. So basically, in whatever the for example, the typical old-fashioned way to measure the radiation efficiency is to do survival curve of cells in vitro. And in that case, you can't, basically what you count is the capacity of proliferation of the cell. You consider that a cell is dead when it's not able to proliferate. Even if it's not dead per se, there can be still some activity or things like that. But the main how to say the way biology sees the thing is that a cell needs to be able to divide and proliferate to be considered as acting normally. But it is true that we don't want the tumor to proliferate more, or the proliferation of the tumor to be spared. That's why it's so important that we do all this experiment in a tumor context. But we really want to do it with a tumor which is really in the lung and not tumor cell in vitro, because that is easy to do. But I mean, the thing is, we want to prove that there is no difference. So this is really difficult, because if, for example, if we do an in vitro experiment with tumor cells and we see no difference, yeah, okay, but could there have ever been a difference? Because in vitro experiments with flash, it doesn't really work. So if we do, we have done that a lot already, irradiation of tumors that are injected under the skin. So you have kind of a ball of a tumor, but it's really under the skin. When you touch it, you really see that it's not more inside that under the skin. You could take the tumor like this. So it's better, but it's still not very physiologic, because I mean the link with the rest of the organism is maybe, well, patients don't have subcutaneous tumor, so that's why.
Thank you, Doctor. The other question that I had is, as far as I understood, there are many challenges passing from a mouse to a human, right? I want to know how much is the impact of the size of the body, taking account that we have the electrons with relatively low penetration in the tissues. So maybe you can get easier lung of a mouse in comparison with the depth that we can have in a human body.
Yeah, absolutely, for sure. And the size is, well, first, it's a mammals, but it's still a small mammals, and well, very simple. So yes, for sure, a mouse is not a human, and it's still quite far for humans. The advantage of the size is that when we use low energy electron, we are still able to irradiate all the lungs. So let's say the energy of the beam is more or less scaling with the size of the mouse. So for that, it's not too bad. But again, the goal in the end for the Institute Curie is to have this very high energy machine. So in that case, we will have deeply penetrating beams. So we will be able to treat bigger patient. So for the moment, it's not in the project. What is defined in the current project is to go up to experiment on mouse. But of course, then after this first project, we will continue. But it's not decided what will be the next step. But what is possible, what has been done already in this kind of case, is either to treat some pigs, which has a quite. But in that case, we really need. I mean, it doesn't make any sense to treat some pigs now with low penetrating beams, because so we need to have the machine first. So either pigs, or to go, which is, to my opinion, more interesting, to go for veterinary trial, as it has been done. I don't know if you were there previously. It has been done already for flash radiotherapy in different centers, but not in the lung. So, to be honest, I don't know if dog and cat have some lung tumor, so we would need that. But yes, we are discussing with veterinarians to plan what we can do, what kind of cat and dog patients they can have, and in general, the veterinary trial are. It's a very nice modality, because I mean, we will really treat them, because the veterinary in France is sometimes do radiation therapy on animals, so they know how to do it. And for the owner of the animals, it's a way sometimes to give radiotherapy to the animals that they wouldn't do because it's very expensive and it's not reimbursed. So maybe even if it's a win-win situation. So yes, maybe that we will go for that if we have the machine.
Okay, okay. Thank you very much. Okay, thank you for your talk. So I wanted to wrap up all the talks that we have had during this conference. We have touched a lot of different topics from flash therapy, of course, and we have opened with flash and closed with flash. We have also touched a lot about the adaptive radiation therapy, that it's getting strongly being used lately. We also have touched some topics about intelligence and artificial intelligence in several topics, from radiation oncology to imaging. And I think that's more or less a very fast overview of the works, of course, also 3D printing and the importance of this work. So we have tried to cover from radiation therapy to imaging. We would like to have had more about nuclear medicine, but the schedule was very tight. And as you have seen, we have covered a whole week with different topics. I have forget about the magnetic the nanoparticles application, magnetic nanoparticles applications, also for radiation therapy and for imaging, right? So far, I don't know what else do we have seen. I don't know, but well, hadron therapy. This morning we have two very good talks and very strong in physics about hadron therapy with Jonathan Osorio and Pamela in the morning. So I don't know what else, what other topics. So we have tried to do our best to give you an overview of the last tendencies in medical physics, in which direction it's moving this field. And I wanted some words from our director, Maria Cristina, who has been, luckily, she was unable to be online, in person, but she has been online the whole time. No sé si se puede conectar. Ah, pero no sé si tiene voz o video.
No.
Ah, ahí estás. She was
Yes.
closer than with.
Can you hear me?
Sí, sí.
Okay, thank you. Yes, I would like to say thanks a lot, all the people that to contribute for this workshop. We wanted to prepare some subject about the latest trends in medical physics, and I can say we done. We just it. Thank you so much, all the conference, all the speakers. Excuse me, all the speakers with all their disposition to contribute to our academic level. And finally, I would like to thank the Faculty of Science that they help, the directive of this faculty help us financially with the money, and the academic vice dean for their management of transportation to National Cancer Institute workshop, all the collaborators, Daniel, Juan Diego, all the people like Professor Luis, Professor Andrea, Dr. Brigitte, all the people, Professor William. I don't I don't want to forget anybody, but thanks a lot. This is a team that we had. Thank you so much. Okay, that's it. Thank you.
No, also Jonathan McAllister, who has been allowing people
Yes,
to get
McAllister was a very big and strong help for us.
Ian Rossi, who was also one of our PhD students, he also gave a talk, and he has been also behind the curtains like the other students, or well, Tatiana too, who helped us with the web page.
Yes,
right?
yes, of course.
Which was
Oh my God.
a very big handicap, because without this web page, the university didn't allow us to begin, and didn't give us any money. So, so we have been working on that direction. For those who are online or also in situ,
Yes.
I wanted to ask you, Marquesina, if you can explain the certifications.
Yes, the next week with Daniel and Tatiana and another guys, we will send to different participants with 80% of assistance in our workshop. We will see if we can do some exception. I'm not sure, but we will try to see which people accompany this workshop in many conference, and the conferences and the speakers, we will send their certificate to participate in this workshop too. The next week, please. We will send.
So yes, we need some time, because we have had around 20 people here, more or less, sometimes 30, sometimes 10.
Yes.
But online now there are only 38. Okay, but this morning there were 66 in the first
Yes,
talk.
around 66. The average is 66. Excuse me that I interrupted you. Yes.
Yeah. So we have had even more, around 52. So it's I think we have tried to reach and make it easy to everyone to get access to this information. This workshop was in principle intended for students of the Master of Medical Physics here in Colombia. But as the time passed, we decided to open and broaden to everyone, not only here in Colombia, but also around the world with this connection. We have had a lot of people from India, which was crazy to have. For us was fascinating. Well, crazy in the sense of fascinating.
Jamaica, Cuba, from Latin America.
Yes, this morning I was checking people, and was from Jamaica, Cuba too, where we spread the word in Alfim WhatsApp, which is a very, very large amount of, there is a large amount of people. And
from Colombia. We have many.
Of course, from Colombia, yes. Some of the students also who were also speakers here, I have seen them connected through the other talks. And I think we have reached more or less our goal. So the certificates will take some time, because we have to check the assistance of everyone. I mean, if you have been participating 79%, so we can make an exception. No, this 80% is not so a ground truth. So we will try to be flexible in this sense. So I mentioned in this case of India because people should be sleeping, but somehow they were connected here. And well,
Professor Luis, another thanks that we need to say is Erasmus program.
Yes.
And Professor Carlos Eduardo Sandoval.
Yes,
thanks
Carlos
to him,
was supposed to be here around
Professor Sophie.
3:30. Yes, I was this. Yes, so we have two thanks to the sponsors. The biggest sponsor has been the science faculty, The second biggest sponsor has been the Erasmus program, bringing people here. We hope to also be sponsored by ECTX, although we still don't have the money. We have already wasted it, so cross fingers.
Thanks to you. Thanks to you.
And another big sponsor has been Brigitte with empanadas.
Yes, all the help from Dr. Brigitte. The workshop, it was so good.
Yes, so
Her workshop.
Of course, special thanks to these two girls who had taken free time from their other jobs to share with us. Well, I wanted to let you know that we have been we have had this morning or this afternoon or at noon we have had a short talk with with Carlos and Luis Demetrio, who are the Erasmus the Erasmus representative here, and Luis Demetrius, the head of the curricular, searching options on how to continue sending people to work in, for example, with Sophie again. There are some things that we still are considering because the Erasmus program has been finished. We are trying to recap them again, but we still have the other options to continue working with Institute Curie. One thing that we also have to overcome is that being able to stay longer, because I think in 1 or 2 months it's been it is a very tight and very demanding, and you cannot develop as good as it should a research. So we are figuring out how we can balance the medical practice with the stay out abroad. So we have to find out how can we solve this, but the idea is to stay longer. So longer, of course, that also means more money because students like to eat 3 times a day and and all these things. So they also eat, they also have life, and we want to take care of their mental balance. So we are looking for.
Can you propose that it's maybe good to hear to Professor Sophie and Professor Guillermo their impression about Bogota, Colombia, for Professor Sophie, and Bogota National University for Professor Guillermo? Maybe you want that they can to say some words about that.
Yes, you can give us a feedback of your stay
Yes,
this week.
Please.
Sure. No, well, we come there so she can see me because. Dear Maria Cristina, yes, it was a pleasure to be here for sure. It was my first time in Colombia, my first time in South America, and it has been great that it has been with all of you. Well, I had the pleasure to, thanks to Luis and Andrea, to visit a bit Bogota last weekend, and hopefully a bit the weekend to come. And it was fantastic. Really, that is a very nice city, and I take this opportunity to really thank very warmly all the people that have taken care of me to drive me everywhere. So particularly William and Luis and Andrea, because otherwise I would have been a bit lost without them. So thanks a lot.
So, Guillermo, few words. Pues en español porque esto también es para... Estamos ya en la parte...
Bueno, para mí ha sido una experiencia bastante linda el haber vuelto a un congreso en Colombia después de vivir muchos años fuera, después de 13 años fuera. Y sobre todo me sorprendió la visita al Instituto Cancerológico por los equipos que tienen y por la labor social donde está impactando ese tipo de equipos. Eso para mí fue realmente muy lindo, muy impactante y emocionante sobre todo, porque son equipos de primer nivel en situación, para personas en situación muy vulnerable. Entonces, eso para mí fue muy importante y muy emocionante. Y después, bueno, compartir un poco acá con ustedes, conocer qué se está haciendo. Apenas llevo 4 meses en Colombia, así que me estoy acomodando. Y nada, agradecerles la atención y la buena disposición.
Gracias. Thank you. So I'm going to translate this because I think it's very important what he has said. The most impressive part was the visit to the National Cancer Institute. I was thinking how to translate this. Because they have a very new, very high level equipment for radiation oncology. They are also renewing the part of imaging with double energy CTs. They have 2 of them. They also had, well, the brachytherapy unit with high dose and low dose. The radiation oncology part had a Radisac, had a Halcyon. They still have the former Kleenex, which work with total body radiation, rotating the patient, not with the Stanford protocol. They also showed us, they had also an Electa, I don't remember the Versa, see? A Versa Electa. So, and the most important is that this equipment is for the most poor people in Colombia. It's open for everybody, but we're speaking about a very high level clinic for open to everyone. So, which I think is one of the biggest impacts that we can show from here and to be proud of. Carlos, ¿todo bien? So here we have a Carlos with us. Any word? Well, no? Okay, then Carlos has nothing to say. I think this is time for the last goodbye. So, hora de decir adiós y vamos a pasar al cóctel. I don't see this in English because if you are online, we'll miss the, yes.
Professor Luis, excuse me, but in 16 minutes, the surprise that we have a surprise.
No,
Maybe in the auditorium
we can,
or not.
Yes, so please stay at least 20 minutes enjoying the
Yes.
cocktail and the wine.
Before cocktail, please stay there. Keep with us.
Ah, no, the last picture with Maria Cristina. Yes,
Oh,
please.
okay.
And I would like
The Yu
everyone,
Takeuchi building.
or if it is possible that the 33 that are online can be shown too. So everybody can be
Oh,
everyone
yes,
who's in
please.
can
Please,
open the
cameras.
camera.
Yes, very good idea. Please,
Before the cocktail.
ayúdenos abriendo las cámaras. Por favor,
Sí,
todos, Guillermo, Roberto, Mari, Edwin, Guest,
pero creo que
Yunis, todos.
no sé cómo que te quiten a ti de estar, o sea, a medida que se abren las cámaras van apareciendo los otros. Ah, le dices.
Sí, señor. Cada vez que entre alguien, abran las cámaras, van apareciendo.
Vale, listo. Bueno, pero no, eso, ya vamos con ese. Dando ejemplo, dando ejemplo.
Hernán, tú
please.
también, señor, por favor, don Hernán.
¿Será que teníamos 30 bots?
Por favor, Luis Cáceres, Gina Benítez, Diana Caterín, José Ignacio, Elkin, todos, por favor.
Yeah, we're waiting for them to. So please, everyone, just turn on your camera.
Yo.
We want a big picture of everyone. Que por favor todo el mundo enchufe su cámara.
Por favor, abran sus camaritas.
Oye, ¿será que no?
No sé.
¿A que si nos
Macalister, ¿por qué la cerraste? Eso, por favor. Estefanía, Héctor Galindo, Juliana. Yo puedo aquí leerlos. A ver,
Eso,
demos
son.
ejemplo.
Boletémoslos, que vayan. Esto queda grabado.
Ya está activo.
Pero,
Ya está activo, ya la pueden grabar. Prender.
Va.
Ya la pueden prender.
ya pueden prender las camaritas. La tuya también, don Hernán.
Eso, gracias.
Gina.
Así.
Bravo.
Tranquilos que a
Bravo,
medida que van
Jairo.
apareciendo, cada uno aparece más pequeños,
Eso.
que no de pena. Eso, muy bien.
Eso.
Muchas gracias.
Maravilloso.
Solo para la foto, tranquilos. Y luego la apagamos.
Muy bien, Carol. Gracias, María
So thanks everyone.
Cecilia.
Can continue turning on your camera. So, pues vamos el resto mientras.
Estefanía, Georgina, Juliana, Dampani, Epili, please. Jan, bravo, Jan. Please turn on your cameras. Por favor, prendamos las cámaras. Queremos una foto con todos. Luis Cáceres, Diana Caterín, Mari, Jorge Rincón, todos, por favor. Juliana, Sebastián, María Cecilia, Jairo, Jorge Rincón, José Ignacio, Héctor Galindo, Yunis, Alexis, bravo. Súper. Vamos, vamos, anímense. Vamos a hacer una foto bien linda con todos. Gracias por acompañarnos durante toda esta semana.
Bueno, ahora sí, muchísimas gracias por prenderlas. Yo sé que muchas veces es difícil, pero muchas gracias a todos. Y todas. Bueno, pues ya no. Creo que ya podemos desconectarnos y lo que fue, fue. Quedamos pendientes con todo el mundo. Bueno, pues somos de los que no nos conocen, creo que todos nos conocemos, pero por si acaso, pues aquí estamos en el departamento de física, en el grupo de física médica, pero el departamento en general, para seguir ayudando en lo que sea o intentando encontrar y buscar estas colaboraciones. Entonces, pues simplemente nos escriben si tienen interés en algo más en detalle. Y muchísimas gracias por la participación. Pasamos al cóctel, al resto.
Profe Luis,
Dime.
y el profesor, el señor vicedecano Fierro, que nos había confirmado que venía.
Pues había confirmado a las 3:30, pero no sé, no lo he visto.
Pero sería
Le
bueno
guardamos.
que las personas que estamos aquí por fuera pudiéramos ver la sorpresa de ahorita, ¿no? En
Sí,
10 minutos.
Yo creo que sí, yo creo que se puede con aguanta, la sorpresa llega. Porque todavía queda el cóctel. Ahora les digo que esperen unos 10-15 minutos y ya.
Esperamos, entonces van al cóctel y esperamos para que llegue la sorpresa.
Sí,
Okay.
vamos a enviarla por correo. Más adelante vamos a enviar un correo con la información de cómo ha sido una pequeña recapitulación y con algunas fotos de los invitados y esta foto de clausura también. Vamos a compartirla con todo el mundo. Listo.
Muchas gracias. Vale.
Nos debemos un vinito, María Cristina.
Celebramos, seguro que sí.
Listo.
Chin chin. Salud.
Muchas gracias. Gracias,
A
Carlos,
ti.
por venir. Te cogí a bocajarro. Sí, no está. Pero bueno, ahí vamos. Sí, no, sí.